Bijit, Bijitri, you just need to use your login credentials from college. Okay, good morning, everyone. This is Sankat from Synopsys, and today we are starting our 3-day workshop on TCAD tool. Along with me, I have uh, three of my colleagues who will be driving today's session. It is Samir Shah from Synopsys, Sushant Mittal from Synopsys, and Narendra Rai. This session starts from 9:30 onwards till 12:30. This includes theory plus hands-on, but hands-on is more on a demo mode. So, and this recording will be available on the Chipin portal. So if you have anything, you can just go back and watch the recording. So I'll just hand it over to Sushant to take this forward.
Okay, thank you, Sankalp. So good morning, everyone. I'm Sushant Mittal, and I'm here to provide you an overview of the Centaurus TCAD. I hope my slides are visible. So um, I believe most of you have seen the agenda, and it looks something like this. So today we are broadly covering the topics of today's 21st October. We are covering the topics of Centaurus Workbench and Centaurus Visual. So these two tools form the backbone of Centaurus TCAD. And Narendra Rai and Sameer will be conducting the session. Before that, I'll be giving an introduction session on Centaurus TCAD. I'll try to wrap it up in like half an hour. And so you will see this, and then we'll have a Q&A session at the end as well. And then tomorrow, 22nd October, the plan is to conduct a session on Centaurus Process and Centaurus Process Explorer. And we will be building a simple NMOS inverter from scratch and also looking at Centaurus Process Explorer for a FinFET-based CMOS inverter process. And on 23rd October, Narendra Rai, along with Sameer, will be giving on a session on Centaurus device. How do we simulate DC output and transfer characteristics of a MOSFET, which was constructed a day ago, like that. And so these are the speakers of the workshop. So Sameer Shah, he is managing our TCAD team in Synopsys. He's a MSc Physics from IIT Bombay and MTech from IIT Madras in Solid State Technology. He has been with Synopsys for 18 years, and he has also worked at Bharat Electronics for 8 years. He is a TCAD veteran and knows Centaurus TCAD, I would say, more than like anyone I have seen. So I mean, it's a very good opportunity for you guys to learn from him. The sessions will be conducted also by Narendra Rai. He has finished his PhD from IIT Bombay recently, and he is a master's from IIT Jabalpur, and he has been with Synopsys for around half a year, and and but he knows the tools very well, and as he will be sharing today, tomorrow, and day after. And I'm Sushant Mittal. I also have a PhD from IIT Bombay and a BTech from IIT BHU Varanasi. I have been with Synopsys for about 1.5 years now, and I've also worked previously at Lab Research, Applied Materials, Micron, and NVIDIA companies. Yeah, so before we dive in, I also have a slide on like how do we make best use, like how a participant can make best use of the workshop. As Sankalp mentioned, that it is conducting that we cover both theory and also a demonstration. So demonstration is done in a calm atmosphere. So therefore, we are like it's kind of in hands-on mode, even though we will not be accepting direct feedback from you. So we will be conducting it or showing the demonstration in a calm atmosphere, in the sense that you will have time to follow the steps which are being shown, and we will not be showing most likely like a lot of steps in one go, so that you have time, and also like if you follow one-on-one, it will be very good learning experience for you. That is my suggestion to you. So we encouraged all the participants to make use of Centaurus Ticket Access they have, because we'll be starting from there, like how do we start the tool, invoke the tool, and then do step by step like different application. Okay, someone is saying my audio is not proper. Can someone comment? Is it at my end?
No, Sushant, I can hear clearly.
Okay, let me just say.
Even I can hear clearly, Sushant.
Yes, sir. Voice is audible, sir. It is clear, sir. You can proceed, sir.
Okay, sure. Thank you. Okay, yeah. So what I was saying is that we would definitely encourage everyone to, do what you are seeing parallelly so that you can make best use of the workshop. And if you do that, we would expect participants to, at the end of the workshop, using a layout and a process flow, they can build a device using S process and also Process Explorer. That will be covered on day 2. And you should be able to simulate on the devices which have been built, perform different characterizations such as IDVG, IDVD, CV, whatever is needed. And then you should be able to write several SVisual scripts to generate publication quality plots interactively, and also perform several characterization on the generated plots on the data. And then I have forgotten to mention, but you should also be able to use Centaurus Workbench very, very effectively so that you can use different tools. So we are giving you a very quick, also a detailed overview of all the tools which can get you started on the on this tool on Centaurus TCAD very, very nicely. So yeah, so that is our suggestion because if you follow this, then it will be very good. Even though recordings are available, but we will not be available later on. I mean, of course, you can email us the questions, but like we can also take your questions later on, right? And your doubts can be cleared. So better to make best use of this possibility, of this opportunity, I mean. So today, the agenda which I'll be covering in the next 20-25 minutes. I have like only 17 minutes remaining, but I'll probably take a little bit more. So what is Centaurus TCAD? I'll touch upon that. Before that, some history of the semiconductor devices and then some device exploration using Centaurus TCAD. So there are different tools which I'll be talking about, like S Process, SDE, Process Explorer, Device Simulation Tool as Device. You will be diving deep on these tools, but nonetheless, I'll just briefly mention. And then framework for seamless operations are different tools. And then also how do we visualize structure and different internal fields of the device using SVisual. This is something I'll be covering tomorrow, like as process deep dive. And so that is not covered today. So we see that semiconductor industry is currently booming, as we see like a lot of fabs are being announced in India, and they are driven by like for example the AI because AI need data centers and also a lot of compute power. So all this is based on semiconductor devices and different kind of devices like logic devices, memory devices for data are being used. And similarly 5G, IoT and data centers are there. Like basically a lot of drivers are there for the semiconductor devices. Like we have seen the transition going from planar to FinFET around 10 years ago, and now we are seeing the transitions like in the last couple of years going into the gate-all-around devices. This is like if you talked about it and like in the industry about 20-25 years ago, this would seem impossible, but this has happened, and we have seen this in our own lifetime. And as a result, we can see that the global semiconductor market is like is just wait a second. This is annoying a bit. Okay. So the global semiconductor market is like increasing exponentially, and we are seeing a rise in India as well. So this is the right time to be in this industry and conduct research. And like academia forms the basis of like any research, right? Like for example, this FinFET device, which came in 2012, Intel made the first FinFET. This was invented in 1992 or 94. The first paper came from UC Berkeley, and they fabricated the device, but I'm sure they firstly did there was not very popular TCAD at that time, but they must have done some numerical modeling of the device. There are some papers, but it was done in academia. I'm just saying that because most of you are from different academic institutes. And similarly, automotive, we see that more and more cars or like whatever automotive we see are semiconductor driven nowadays. So there is a lot of demand of semiconductor devices, power devices, logic devices, memory, RF photonics, like you name them, and we have a semiconductor device for that market. So basically that is the driver. Now question comes that where is the role of modeling and TCAD. So any design which we do, or like any research which we do, or like for a technology. So there are two, broadly speaking, there are two buckets in which this is done. One is technology and another is design. So in technology, we start with different process assumptions. We first of all narrow down on like which transistor we want to work on. Like for example, FinFET, gate-all-around, nanosheet, Fogsheet FET, and then how do we make the device? So that necessitates the, like it should be patternable, like whatever CDs are required, critical dimensions are required for the technology node. That is also technology which we have to figure out. And then we also need to make its back end of the line and back end, the middle of the line and back end of the line stack. And we also have to ensure, because this is important for interconnects, because this is the front end of the line device and it has to be connected in a circuit using this technology. And then this technology also is going through a lot of innovation in the sense that the copper is running out of steam now, because copper was a material which was very low resistance. But what is happening is that for like, if you can see this, maybe I'll just magnify a bit and show that F 20 nanometer CD and below, the copper is essentially resistivity is increasing, so it is causing like performance loss. So therefore, ruthenium is the material which has been introduced, and so this is the innovation which is happening at the technology level. This is given as an input to the standard cell design. Now this is the circuit level which we see. So standard cell design. So there are various standard cells and or like XOR many inputs, right? And then we do library characterization, and using that we do a design, and then we, after all this, we do a PPAC and also T, like how is the performance, power, area, cost of that product, and also time to the solution. So PPACT is done, and so this also goes as an input, like based on this, that maybe some technology is not giving as much PPAC. Then we like focus on in either part of this like MOL, BOL transistor, and after this, then we give this design world SPICE model integration scheme, transistor architecture to work on, and here like TCAD plays an important role in downsizing the options for transistor and also the MOL, and in fact like we can do using TCAD this entire DTCO flows, like we can go from transistor to circuits in this essentially. I'll talk about it either today or tomorrow. So this has been the logic technology roadmap. I don't want to take a lot of time, but so basically we have a planar CMOS device which was present till 22 nanometer node, and now we are into FinFETs like from 14 nanometer node and below, and then we are talking about gate-all-around like 5 nanometer and below now. So this is like, and then at technology front we are seeing new channel materials like silicon germanium instead of just silicon. And then high-k metal gate came in 45 nanometer node. Strained silicon came in 19 nanometer node to give higher mobilities. And then we went to low copper and low K. And in fact, I think I'm missing the slide for, and this slide, the ruthenium, which I was talking about. So now even ruthenium interconnects are being used. So then the different devices are being there, and we are not talking about nanosheet, starting from planar, now going to FinFET, gate-all-around. Now we're talking about nanosheet and gate-all-around. So the logic scaling, logic technology has gone through a lot of advancement, and TCAD has played a significant role in that. So let's try to understand the TCAD value. So this is a typical, let's try to understand this plot. So y-axis is number of TCAD simulations we perform, and x-axis is the stage at which a device is. So initially, a device is in a device research in a stage, like whatever we do in academia, like we do like try to find, right, if FinFET work, gate-all-around work, and CFET, whatever you name, a few people I'm sure are exploring lot of devices, and what device architecture works. So like some significant amount of TCAD simulations are done. Once this is finalized, then for module development, like how do we fabricate the device? What are the different unit processes we need in order to fabricate the device? Then the number of TCAD simulations or support of TCAD increases essentially. Like here, there are a couple of examples like junction engineering. This is one, like that means this is dealing with the process of unit, like process implantation and annealing. Then there is trench optimization, like this is etching optimization for 3D NAND technology. And then once we have figured out, like, using TCAD and of course experiments, what unit processes work, we need to integrate them together. So this is like process integration, in which like basically device optimization, and then also there could be reliability, variability issues. So this entire comes in the bucket of module development and process integration. So then the support of TCAD increases all the more in a typical fab, right, or an industry. And then once the yield starts to mature a bit, we have a risk in the production, but then we, like, whatever the variability are there in the devices, we do different process centering techniques using some TCAD, but now the technology is a bit mature, the number of TCAD support is reducing. And once the technology is in production RAM, the TCAD support vanishes, because then we move to the another thing. And so, TCAD plays like a very fundamental role in order for faster yield ramps and also reducing the development cost. And I'm sure like most of the thing which we do in Indian academia is centered around these like first three pillars. So we play a like very important role, like whatever research, like a lot of research which we do actually goes into the industry and being used. We may not know, but it is being used. Okay, so using Centaurus Synopsys TCAD, we can cover all the different major semiconductor segments: logic, memory, power, analog, RF, optoelectronics. It's a general purpose software, and which using the required physics, as you will see, and required math settings, you should be able to simulate the device which you're looking for. So what essentially is TCAD? TCAD stands for Technology Computer Aided Design, and broadly speaking, there are two parts. Again, like first is that we need to construct a device, because device structure like this. Here we are talking about NMOS transistors, and to construct that, a lot of and you can see also the meshing in that, and then different mesh points, different in order to model this different partial differential equations are solved. Like for example, this is PDE for pair diffusion. Pair is essentially how the dopant which comes, it forms a pair with the cluster, and then it moves together, and in order to get activated, and like after implantation, and also annealing, and then it can give some doping profile, and we can like calibrate it to the experiment. So these are solved on these mesh points. Similarly, this is showing the reactive ion etching, which has been performed, and then a PVD deposition, and then local oxidation of silicon, in order to fabricate a device. It goes through a lot of these unit processes in order for us to construct a final device, and then it has to mesh properly for device simulation. So this is the first part. Then you construct a structure, and then it comes, and it is read in a format called TDR format. And once we have it, then we perform the device simulations, and you will be seeing that in like very much detail tomorrow or day after tomorrow, and in which like you can basically again solve PDEs on different mesh points and for different equations like current continuity equation, Poisson Laplace equation, self-consistently, and so that you can get the potential or like charge distribution inside a device, and also get the terminal characteristics of the device. So yeah. So in process and device simulation, so we do it using a software called S-Process, and which is essentially a virtual representation of a manufacturing process. And we will be having a detailed session on it, and it goes through a lot of unit processes like doping, implantation, annealing, oxidation, etching, deposition, masking. So you don't have to bother about it if you are not aware of these terms today. We will be seeing them tomorrow in a bit detail. So here, for example, I have a process flow on this slide 15 of a 28 nanometer bulk CMOS, in which we have a isolation, then we have gate stack patterning, then we do halo implantation, spacers, silicidation, and then polysilicon removal, dummy gate removal, and then high K metal gate, ILD count. I'm just reading it up, but we will be simulating this entire process, maybe not all the steps, tomorrow one by one, so that you are aware of the format and how it is done, and and you also can get a feel of how this device are constructed. So the key process techniques which are there are like lithography, implantation. Lithography is basically when we want to transfer a pattern which is in the mask. And then implantation is to change the electrical property of the semiconductor. We do either group 3 implant or group 5 implant, like if you want, depending on the doping we want. And then to activate those dopant atoms, we do diffusion and annealing. In order to form the gate oxide or grow an oxide, we do thermal oxidation. And then etching and deposition are used at different stages to create patterns, essentially, in conjunction with lithography. So this is an ion implantation process. I don't want to go into detail. Tomorrow I'll be talking about it. But essentially, ions can go inside and can create and then can come into the lattice, and then they can be activated using activation process. This is an activation process where we have in Centaurus process we have like the kinetic Monte Carlo base or atomistic models, or also have the equations based like analytical formulation of those models for activation. And basically, activation means that the dopant atom which came in as a result of ion implantation should replace a silicon in order to get activated and contribute electrically. So this is for using interstitials. This is using vacancies. So this is a Centaurus process simulator. It's a general purpose simulator, and it has an integrated 3D geometric modeling engine. And we have analytic and Monte Carlo implantation, diffusion, mechanical stress, oxidation, geometric deposition, and etching. So this is like after you have done the doping on a nanowire with some line edge roughness. So you can see that you should be able to simulate these kind of effects. This is BCD device. This is trench oxidation, trench IDB, IGBT, LDMOS, silicon junction power FET. I'm just saying that we can simulate different devices. How does it look? It's essentially a command, tickle-based command file-based software, and we will be seeing the syntax tomorrow, so no worries. But runtime can vary from like several minutes to several hours for a 2D device, can vary from several hours to several days for a 3D device. So yeah, and then we also have a geometric editor. It's called Centaurus Structure Editor. So Centaurus process works very fine when we have a process flow defined. But suppose if you are working on a device where the process flow is not known, but you have an idea, as we many times have in academia, and you guys are aware, and I see a lot of papers on those lines also. So you have an idea of a device which you think will be very good. So in order to get the first cut results, you can use Centaurus Structure Editor. Just to show how that device can be constructed. We will not be talking about it, but we will be showing you where you can find the tutorials in order to construct device using Centaurus Structure Editor. It has like easy to use GUI, and when we don't know the process flow, you can use this. But just a suggestion from my side, like once you have seen electrically that the results make sense, you must show using S process that the device is fabricable. You should have thought of a fabrication flow to fabricate the device, and that should make sense. And you make use of Centaurus process, which the tool which we'll be talking tomorrow, to show that how that device can be constructed. Because many times using this tool we can construct devices which probably are not feasible, or the feasibility has not been explored. And because you are proposing that device, so you are the best person to explore the feasibility of that device, right? So you should be exploring after the initial analysis the device in the process, Centaurus process. So that is just one comment. And we need to just also mesh the structure properly in the regions, so that the different regions which we want to model are properly characterized. We'll be touching upon it a bit tomorrow when we look at the Centaurus process. So like for example, here we have a junction, so we need more mesh points in order to resolve it. Similarly, we have the oxide semiconductor interface here, and so that also needs proper resolution. So we need to add those points appropriately. So Centaurus mesh, we will see some example of it tomorrow, but it is this kind of a syntax is used in order to mesh it. And in SDE, we can use GUI also to mesh it, use to like refine the mesh. what is device simulation? So this is virtual test of electrical and thermal behavior of the transistor. This is done using as device. And once you have the device, you perform using as Centaurus device these characterizations. And we are right now focusing on using the individual transistors, and we saw drift diffusion, Poisson carrier continuity equation, also like heat transfer equations. And the output is several internal characteristics which we are never aware mostly when we have fabricated device, like for example, potential distribution or charge distribution, space charge distribution, things like that. And also get terminal characteristics like IDVD, IDVG, CV, IDVD, and also like the VT roll-off effect, things like that. So again, it is a general purpose simulator. It depends on the which physics to include. We can support different like silicon and compound semiconductors. It has a mixed mode simulation mode also, in which if the compact model of the device is not there and we want to simulate it at circuit level, we can do it using mixed mode. And then it has various transport mechanisms. Narendra will be touching on this in very lot of details, so I don't want to go on, like talk more on it. And the syntax also you will be learning in like quite a bit of detail day after tomorrow. So let's not spend time on it. So Centaurus Workbench is another tool which is being used heavily. So basically, it can connect different tools together in a easy to use GUI, and it can be very helpful for DOEs, optimization, and project management. So Narendra will be touching on this tool today, and along with Samir. And then we have Centaurus Visual. So I'm sorry if I'm it appears that I'm rushing, but like these are just summary, like just one slide summary of what you will be seeing in detail. So because the detail is coming up, so I'm just taking the liberty of running over these examples. So here, Centaurus Visual essentially can help you to visualize the terminal characteristics as you see here, and also the internal characteristics. Like for example, we are seeing the net active concentration. We can also see a lot of other things like the stress in the device, and as I mentioned, electron density and the things like that. And you will be seeing that. You can also write scripts, as Samir will teach today, in order to generate with like very nice publication quality plots using this. Then we have a tool called Process Explorer, which is also to construct the structure. We will have a hands-on session on it tomorrow, so I'll again skip it in the interest of time. We have like a lot of library like examples in a library, and which people can explore, like for example, FinFET, BCD, locus, gate-all-around, things like that. This is one slide which probably I'll spend some time on now. This is a DTCO workflow for a DRAM sense of amplifier optimization. So using like once we have a silicon data, we usually for a technology development we do TCAD calibration, and of course after constructing a device in S process and electrically modeling it in S device. Then we make compact models. We can extract that using Mystic and Garand software coming from Synopsys, these compact models. So that's how, and then you can reiterate it, and based on this terminal characteristics, you can try to optimize the technology. But when you want to go to the design side, then you start with the circuit design, and you can do that in custom compiler, and then but then you also need the back end of the line RC distribution, right? So that is done. The backend structure can be constructed using Process Explorer, and the RC can be extracted using Rafael FX. So you will be seeing some of it tomorrow, not in full extent. And once this is there, then you can combine the netlist, which you had this compact model and this RC of this circuit together, and then you can do different analysis. Like here, I'm just talking about the statistical analysis for that matter. And then you can, using this, you can connect the transistor layout, shape, and also the technology parameters like implant anneal in order to improve the POR. Like for example, here the POR is the sigma VT. So you can connect the technology to the design and circuit parameters. So this is something which like enables, and many industries are using these kind of flows to connect the design and technology together to do the optimization. So and everything is possible using Synopsys TCAD software, and also like this is not part of TCAD like custom compiler, but you can use these tools in order to do this kind of study. So yeah, so Process Explorer we will be seeing tomorrow. So this is our product family for atomic scale modeling. We have Quantum ATK Nano Lab, and Centaurus Materials Workbench. And for process simulation, we have Centaurus process, which we'll be covering in this workshop. Centaurus topography is not covered. And TCAD structure editing, as I mentioned, for basic study, we have Centaurus structure editor. This is also not covered, but we have very good resources. If you want to get started on this, we can point you to those. And then for TCAD device and interconnect simulations, we have Centaurus device, which will be discussed in a lot of detail by Narendra. And Centaurus interconnect is there, and Rafael is there, which will not be discussed. I'll mention about Rafael a bit tomorrow. And then process emulation is done using Centaurus Process Explorer, which I'll be covering in detail tomorrow. Then like TCAD environment tools, we have like a couple of them, Centaurus Workbench, Centaurus Visual. These is like very important to know so that you can be very efficient in using Centaurus TCAD. So this will be covered today. And then we have TCAD to Spice tools like Mystic, Enigma, Gara, and Random Spice. If you want to go from the TCAD world to the Spice world and do some circuit analysis. So this is also not covered, but we have like good getting started material on this. And it may be covered, we can discuss with Sankalp, it may be covered in the future TCAD workshops conducted for C2S. So yeah, so with this, I end my presentation. So this is thank you. So over to Narendra Rai for the next presentation. I hope I was audible all throughout.
You were.
Hello.
And Narendra.
Yeah. So am I audible?
You are, yeah.
Thank you. Thank you, Sushant. Thank you. So let me first share my screen. So my screen is visible, okay?
Yes, Narendra, you can go to full screen.
Yeah. Yeah. So now I will be continuing from where Sushant left. So so he gave a brief overview of whatever we are going to cover in these 3 days sessions. So now I will be touching mostly this HWB and S visual parts.
Narendra, can you hear me?
Yeah.
Just sorry to interrupt. Can you right click and right click on the work presentation? Yeah.
Okay.
I don't see. I basically want you to use the pointer.
So it's right
Like
clicking.
Alt, I guess Alt L comes. By that it comes. No. I'll just tell you. Just wait a second. Actually, Control plus L.
Okay.
Press Control plus L. Escape here. Escape here. Yeah, and go to full screen again. And then Control plus L.
So
Have you pressed it?
yes, I have pressed it.
Control plus L.
It's not working for me.
Okay. Sure. Anyways, then you can use the other
Narendra,
pointer.
I guess you're using the
Web version, right?
web version. So you can just make a full screen, and
Okay.
at the bottom you will find that option. Just make it full screen. Yeah, at the bottom next to your slide thing, you will have one of 68, right? Just
Which one?
bring your mouse pointer towards the left. No, not on that. Not on that.
So I am presenting from here.
Yeah,
Edge.
you can. Yeah, you can just go to your edge screen.
Yeah.
We'll find that.
So this is my screen. Okay.
Yeah. So at the bottom you will see right behind, right.
Actually,
Okay.
Narendra, maybe you can unshare and share again, right? I think that's where the problem is coming, Sankalp. Sometimes it comes, right?
And no, that's not a problem. It comes and it is hidden between the toolbar.
I see, I see, I see, I see. Maybe Narendra, you can hide your toolbar. Just right click on your toolbar and hide it, and then you will see it. The taskbar, I mean.
Okay.
Yeah. Right click and hide it. Taskbar settings. Hide it. It's there, right? Task view, yeah, just turn it off. The second option on the top.
This one.
Yeah, turn it off.
Okay.
Or this is the one.
So
No, that's fine. You can
yeah,
carry on.
if it's fine, then I can carry on.
Yeah. No,
You see it on the bottom now.
yeah, now you can see there is where Sankalp
The
now.
pointer, the pen symbol, which is the second one.
Actually, Narendra, you have to click on allow first on the top. I think. Can you just choose that allow synopsis? So SharePoint.com wants you to allow. Yeah. And then this taskbar should go away. Yeah, allow it. Yeah. Now you can use the pen symbol. And now when you are on the slides,
Yeah.
Now
Control L.
Control L is not working. If that's not working, then you can use this pen pointer. Yes.
This one, no?
No. This is drawing actually. Don't do that. Sankal, do you know which one is this? Which one of them is the pointer?
I guess it was that pen symbol, but
The
that's
pen
fine.
is draw actually. Yeah.
Yeah,
Anyways,
that's
we
fine.
can
And
we
yeah,
can use other pointer.
if it's fine with the
yeah,
participant,
sure.
then we can move on. Okay. So should I start?
Yeah.
Okay. Thank you, Suren. So basically, SWB is your means graphical front end, which will integrate all these CentOS tools. This means starting from building up your structure, then doing electrical characterizations on them, or simulations on them, visualizing your simulation results. So CentOS Workbench does the job of seamlessly connecting these tools together so that you can efficiently build your experiments and run your simulations. It allows for parametric analysis, means you can, instead of using hard-coded input files, you can use parametric files, so that means efficient connecting between the tools will be, it allows for efficient connection between the tools. So this is what I am saying, means, so these are your various TCAD tools, means, which have been arranged in, for example, in this figure, horizontal manner. They allow you to make a, form an experiment over here. So these are various toolbars which you will see when you open your SWB window. Now, how to get to this window first? So you need to open SWB through your terminal. For that, you need to have an installed version of CentOS. Then you need to wherever and wherever in whichever directory your CentOS has been installed, you need to create one home directory, and you need to point your CentOS and database environment to that directory, so that then you will be able to use your CentOS tools. And make sure that whatever directory you are going to point to, this HTTP environment, you should have right permissions to that. So here I am showing this. So this is my HTTP directory. So once this you have the directory and you have set your environment, and then when you enter this command on your command prompt, swb ampersand, then you should be able to see this window. So as I said, once you type this command and press enter, then this is your SWB window which opens up. So this is the DB. Here you will see the DB folder. So whatever simulations we are going to perform, we will be doing this within this, under this DB folder only. This is the main window of your CentOS workbench. So now we can change the
Narendra,
view of this.
Narendra,
Means we can change settings that how this window
Narendra,
yeah.
can you go back to previous slide and maybe wait for a couple of minutes? Maybe if people want to, if they're doing it, then they can just try to do it parallelly, right?
Yeah,
Wait.
if
Yeah,
means
yeah.
people can try login in means
Yeah, I mean, you should give some time to them.
okay.
Just a point. Yeah.
Yes. Yeah, it would be good if they log in into their accounts and they can if they can open this HWA window.
So what we are planning is that we'll give some time so that if participants are doing parallelly, then they should be able to do. So we will be pausing and moving forward like that.
Yeah. So please try it out means in your command prompt. If you have means CentOS installed, then please set your environment to directory to your home directory, as I have set it for this DB directory. This is located at this. For me, it is located here. So once I set my stdb environment to this directory using this syntax, and then afterwards when I enter this syntax in my command prompt and press enter, then I should be able to enter into my SWA window. So this is a general structure of the SWA window, how it comes up. Means for you it will come out as a blank. So here I have opened a project, so it's looking like this. For you, when you open it for the first time, you will see a blank window here without any tools. So I'll move forward. So as I said, hello.
Yeah, you can move forward.
Yeah. So as I said, means we can change these settings, means how this window is rendered, how it looks. So for that, we can go into this means edit in preferences. For example, we can set this PDF reader, whatever PDF reader of our choice, then internet browser. For me, I have set my editor to JEdit. Then, so here are you will also see means in your installation directory where means different things like materials DB or manuals where they are located there. You can see here. So now this I will just means I will just discuss here. Then we'll see it means I'll show it here. Means we can also attach some projects as roots to our DBs. For example, means we don't want to clutter means since as I said we will be doing our simulations under this folder. But if you don't want to clutter this, then but if time and again we want to access some other projects as well, then we can attach those projects as roots. That we can do there over here. We can attach their path over here, and then we will be able to access them from SWA window. So here I'm just showing how to set the preferences for your SWA window. So starting point. Now, if you people would have logged in, then we had shared with you some files to start up with. So, for example, as I said, means once I have set my this DB directory as means I am pointing my environment of CentOS database to this directory. Now, in that I have, for example, I have created one folder named this TCAD, this folder. Now we have shared with you some files. In that you would have seen this .gzlp file. So in order to start our simulations, so we must first unpack this .gzlp file so that we get the required project. So just click on it or click open. So it will means ask you what you want to do. Then you can just click extract. I have already extracted it. When you click on extract, and the file will be extracted in this directory, and you will see this one. I would encourage means you people to just do this if you have already. So I would encourage you to just in your DB folder, just directly you can copy this. So how to do that? Yeah. So what means in your once you are in your DB directory, then you can here you can open a terminal. Either go to extensions and open a command prompt here, or means just means highlight this, click here, and just open a command from using this thing and this icon. So you should see means you should see something like this on your screen. So in this way, you can just for example, I have created one directory here, and then I have copied. So wherever you have downloaded your .gz file, just copy it to this under your DB directory. So once you have copied it, then you would be able to see it in your in your folder. Then as I said, you just click on it, double click. So it will give you options what to do. Just extract it. After extraction, you will see this extracted project. So this is for me. I would recommend at least you try these steps. So once, so that we are in this environment now, so that we can move forward with our simulations. So so all these steps are discussed in this slide. Now again, this is exporting, but we can do this afterwards once we have done some simulations. But it just says that means once you have done, you have worked on some project, then you can just export it. This is the sequence that you should follow, and then you will be able to export. So this is the way means we had shared this .gzv file with you. Means we had created one .gzv file, then we had shared that file. Now how to start with the simulations means if somebody means how to explore this. So once you are into this SWV window, then you have some help means from where you can access training materials, tutorials related to various tools, TCAD tools. So for example, so when you click on this question mark, this is help. So you will see this documentation, this TCAD related documentation. So this is nicely sorted, means depending on various tools. From here you can access documentation. Then so when you click on this, so this is your training material. So when you click on this, you will enter into this window. Here you will find many examples and nicely explained, so that you can get a start. Means if you're a beginner and you want to learn various tools and TCAD tools. So for example, as Sushant will be means covering tomorrow as process, then today I'm talking on a workbench. So you will get many examples here. You can learn from yourself. So it's like this. So you have enough help, self-help to get started with TCAD. So we also have this Python interface. So that means, as Sushant already mentioned, that means the scripts which are used for these tools, various tools, they are identical, but we also have this interface for Python as well. So that these tools, scripts can be written in Python as well. We have SVisual in Python. So Python interface is also available. Now, so I showed you that you can go to means there is already help available over there, but also within this interface itself, we have this application library. So once you click on this, you will see a lot of means application-based examples here itself. So for example, in getting started, you have examples means on S process, SWB. From here also you can start learning basically. So in these examples, for example, if I suppose I just want to if I just want to see regarding some information of some projects, so that this so this documentation is available for projects under this getting started. You will get you have link for this HTML based documentation, so you can reach to these documentations from your SWB environment as well. So, and in addition to that, so for this you are getting this HTML based documentation under application library itself. For example, if you want to see, for example, CMOS application, you want to see some project over here. So you, for this, you can directly see documentation here as well. So there is one GREADME file over here in that folder. So you can also go through this. What is this actually documentation about? So you have access to materials from within the SWB environment itself. It's a very good place to get started, to start learning. Next. So as I showed you in the getting started directory. So for any project, if you want to see what that project is about, information editorial. So you have HTML based documentation over here. So there are many examples application library in the application library. This is a very good place to start learning CentOS. So this also means, as I showed, for projects under this applib, you have direct PDF files as well. Now, so how do we start wins? Okay, we have various projects, application based projects within under this library, applib library. Then, but how to make use of them? So, for example, if I'm getting started, I want to now understand SWB using some example. So how should I do this? Now, as you will see here, these are only these projects are only in read-only mode. So if you want to work upon this, if you want to run this and make changes in them, then you need to first copy this project under your DB directory. Then, so for example, see, I have already made one copy over here, and then I can, and then I have write access to this project. Then I can make changes to it, and I can carry forward with my simulations. So you, as it's shown over here, you just make a copy of the project under your DB directory and then work upon it. Now, so once you have opened some project, for example, I have opened this one here. So here I'm actually in the runs. I have already run it, but you also have options to just pre-process it or run. So running will also most of the cases it will pre-process and then run. So in the pre-process, it will just pre-process the input files. It will not run it. So pre-processing and plus running. Now regarding the structure, how are the projects? For example, I am talking about this project. I have taken this example. So what's the structure? So this you can get information regarding the structure of a particular project from either when you see your title bar. So from there you can see this project is of traditional structure, and this traditional structure is also highlighted through this icon as well. So this symbol you see, this is for traditional structure. So we have two kinds of structures, traditional and hierarchical. So in traditional structure, your input files and other files which are needed for successful running of your simulations, as well as your whatever simulation results are generated in the form of log files and your various IV files and TDR files, they are all located within the same directory only, within the same folder. So for small projects which are of smaller sizes, this is very good. Means we have all the files at one place and it's efficient to work with. However, as your so here I am showing just one experiment, but once you start working with means these tools, you will keep on adding experiments, and overall project size will go on increasing. So in that, when that happens, then this traditional mode or traditional structure might will get slowed down. Means when you try to perform various operations, it will start. So its speed will decrease a bit, and also means for example, you have these tools in your project, and if you want to add some other tool over here, so just a minute. So view tree options, show node numbers. So for example, I have this project, and now I want to add some tool over here. So when I add this tool, this node numbering sequence will change. Now, when I want to renumber the sequence so that everything is in order, numbering is in order. So that is not. So this structure will not allow you unless your output your files, whatever files you have generated, you will lose those files. Renumbering is not allowed in this structure without losing the files. So this hierarchical structure overcomes this, because the input the files which required to run your simulation, like input files and other files which are needed for the simulation, and whatever results you obtain after simulations, they are placed in under different folders. So in this case, now your known renumbering is possible without losing your simulated data, and you can convert from from traditional to hierarchical, but conversion in the reverse order is not allowed here. So you cannot go from hierarchical to traditional. This is an example which I was just talking. For example, I added this tool as visual tool. So when I added this, so see this numbering sequence has changed. Now, okay, before this, so in the traditional mode, how to, an easy way to recognizing that this is a traditional mode, that you can set colors of this background colors of your cells. So for example, hello.
Yeah, I mean, there's a lag. I think we were not seeing your project. I mean, if you are showing it.
Now is it?
Yeah. So please be careful, like what you're showing, Yeah.
Okay. So I'm just saying that. So we are now we are familiar with traditional or hierarchical. So I'm just saying that, for example, so this traditional background is is looking like grayish. Now, I have converted this for demonstration purpose. I have converted one of the project from traditional to hierarchical, and that can be recognized from the change of background color to this bisque color. Then I added this tool to my simulation flow. So now you can see that this node numbering has disturbed. So this hierarchical allows you to renumber the nodes without losing this So this means simulation data is also there, and now my nodes are renumbered correctly. So what are these colors of various nodes? Hello.
Yeah,
Is
go
it
ahead,
fine?
Narendra. Yeah, go ahead,
Yes. Yeah.
Narendra. No problem.
Yeah. So what are these various node colors? So they show what's the status of each node. For example, if when you will open means new project which is not in a run state, so all the nodes will be of white color, and once you start your simulations, then those nodes will be queued for running. Then so the nodes which are queued means waiting in the sequence, so that they have this green color. Then the ones which are ready for execution, then ones which are pending to be for their jobs to be submitted, then those which are running, the nodes which are running, they will be of blue color. Those which are finished and successfully simulated, their color will turn yellow. The nodes which have failed, their color will be red. And if you abort your simulation in between, then these unsimulated nodes, so that whatever aborted and the node for which you stop the simulation, so it will show you this pink color. So these are the various coloring schemes for various nodes showing the status of your nodes during the simulation. So one way of running this is just run it from here. Means once you have selected this, and that means double click, and you can run this project from here. But for example, if you just want to means run only few nodes only, then that is also possible. That you can just select those nodes, and then you can run this. So that is also possible. Just select the nodes which you want to run, and then click run. So only those nodes will be run. Now, after the simulations, if you have extracted, means you need to means include those whatever electrical parameters you need to extract. You need to include those in your scripts. Once the simulation is successfully run, then whatever electrical parameters you have extracted in the simulation, they will appear in the right side of this your table. Now, after we have completed our simulations, how do we see the simulation results? So
Narendra,
yeah.
usually there's a lag, what you're
I-
doing and what you're showing. Just wait for some time. Like you can pause on the screen and when the result has come and just show. Like right now you're showing the slide, but on the workbench it took some time. So maybe you can just stay there and just show that the results have come. And
Okay.
then there is a lag a bit. You just wait.
Okay, sir. Okay, sure. Okay. So this is what I'm talking. If we have extracted some electrical parameters, which for these we include in our scripts. Then when the simulation is successfully run, then the generated out means parameters will be shown in this section of your window, HWB window.
We don't see your SWB window right now. Now we see actually. Yeah. Now you say.
So this lag is quite a bit then, I think.
Quite a bit, yes.
Okay. Now, once we are done with the simulation, now we want to see the results. So the simulations from S process or structure editor or CentOS device. So all these, the results which are generated, which can be viewed through S visual. But before that, let's also see means. So once your simulations are successfully run, so you can click on any of the means yellow node which represents your runs the node which has successfully run. So for example, So I'm slowing a bit because as Sushant is mentioning, means it takes some time for my,
Yeah, it makes sense. I think you should slow down. It's okay.
yeah. So for example, I have this simulation has successfully run. Now I want to see the results. So double click on any of these simulated nodes. So in your out file it's showing means whatever the simulation step, whatever processes have gone through, means it gives an information about your run simulation. These are the various files which are generated during the simulations for that particular node. So this numbering means, for example, n node number, then this is tool specific prefix which is added to that file name, and then the extension. So for example, so this is the pre-processed file which is actually run. Run by the simulator. Will not not going to detail of this, but just trying to show means when your simulations are run, so these node specific files are generated, which from where you will see means the output as well as whatever input went into the simulation. Now, how to visualize the results? So to visualize the results means we have this visualizer called CentOS Visual, and this tool will be used to visualize whatever results we generate from various tools like process, device, editor. So let me show you once. For example, I have simulated this transfer characteristics. Now I want to see whatever various files, output files which are generated during the simulations. So I will highlight this node. Then I will go to I will go to visualize results. Here you can visualize depending upon whatever you want to visualize. So if you want to visualize these IV characteristics, which are XY plots, or if you want to visualize TDR files, which are structure files, so you can visualize it from here. Or if you want to directly instead of choosing, you directly want to visualize. So this is a quick visualize, which will open all the visualization frames. So here, see, he has this quick visualize has opened the structure file as well, which has been generated after SDY simulation. So it's also showing me this XY plot. So it will not automatically plot for you because in your in your plot file you have various data, means you have drain bias ramping, gate bias ramping, everything. So you need to choose it from here, what you actually want to plot. This, how to do this, we will see this later when we will discuss as visual in depth. So as I said, you just click means highlight that node and you have various options. Now, and one more option, I hope my SWB visible, SWB window is visible. So one more way is I will specifically write a script, a visual script to plot simulation results of my, means whatever simulation results of I want. So for that, when I highlight that and I click on this run selected visualizer nodes together, this icon. So this icon will only work for this as the SVisual tool. Whatever script you have written on or whatever your data you want to plot, if this tool is present over here, for this only this this icon will work. So when I click on this, so whatever script I have written to plot this structure, so it's directly plotting me. So these are the three different ways I have discussed with you. Means to visualize through SVisual, means highlight your node and then choose what type of file you want to visualize, or directly go to quick visualize, which will open various visualization frames, means XY plots as well as TDR plots. It will open everything, but XY will open in the form of a blank frame where you need to select the data manually. And this is your means run visualizer nodes together, which is specific to this SVisual tool. So as I said, means if you have written means an SVisual script for generating some output curve, just highlight it and click on it. So this curve will pop up. Now, how to create a project? So let me again first share my SW window. So one method means why I discussed with you is that means whatever means .zip file, for example, in our case, we had shared with you. So you first copied it under your DB directory, then you extracted the file. So after extraction, you have this project, then double clicking on this project and you went on with the simulations. Now, what if we do not already have means and
Sorry to interrupt you, sir.
yeah.
Sir, actually, I didn't got this file cdec underscore C2S file.
Which file? No, this is directory.
Okay.
You might have got this file .zzp file. This file has been shared with you.
No, sir, didn't got this.
So I think I think other I don't know, means it was shared with CDAC team. I don't know, means you can confirm with them, means what, but actually you should be having you should be having access to this file. You can please means contact with whichever means person. Means this .dz file has been shared with you. This was shared. It's okay, means so you can contact the specific person. So I'll move forward. So what if we want to start from scratch? We don't have any project, already built project or something, and I want to build a project from scratch. So just this go to means you can build from here as well, means start a new project and either use traditional or hierarchical, or you can also use this icon and build a traditional or hierarchical project. For example, now if I want to make a new project, so this, if you want to build a project from scratch, then first you have opened a new project. You have selected its type. For me, I have selected it as a traditional structure. This file is temporarily stored here under your TMP directory. Now you can add tools to this project. What I did, I selected it, right click, then add. Let me again do it for you. So right click, add, then go to tools. So here you have various CentOS TCAD tools from where you can choose. For example, in this workshop, we have built a project using SProcess. So for example, if you choose an SProcess tool and click OK, then keeping these default settings, then apply. Okay. So see, this means you have added a tool here. SProcess tool, but this tool still does not have means input files which it should run. So you need to provide the input files to this process. So for that, again, right clicking, get means edit inputs, commands. So when you do that, so you can see right now the command file is empty for this project. So you need to provide your commands, TCL scripts for this command file. You need to write over here. Then when you save, after doing that, you have created this one as process tool. So in this way, this entire project was created for. So in this way, the entire project was created, means adding. I hope my SW window is visible. So in this way, this first tool was added. Then again to add another tool, just select it, add. When you click add, then again you can add another tool. So in this way, this as visual was added. So in this step-by-step manner, all the tools were added, and command files for means initially all the whatever tools you add, their command files will be empty. You need to enter the command files. So actually, we had also shared with you this command files as well in a separate folder, but no need for that since you already have this project. You can just unpack it and run it, and then you already have all the tools with them in ready to be run state. But this is how you start building a project from scratch. This, as I showed, go to tools, then use a tool to generate your structure. You can use SD or S-process. Yeah, then once you have added, so I think so I deleted it. So let me just quickly do it 1 second for you. So I hope my screen is visible. For example, quickly I have added this. Okay. Okay. So now, so this, as I said, this will be under. So this should be under your. So somehow it's not showing, but this, whatever new project you created, this will be under your temp directory. Then when you select that project and click save as, then it will give you an option where to save. Then in that case, you should give the project a name and save it under your DB directory to which you have pointed your STDB environment. This I have already showed to you, means how you can open a Unix terminal, means when I showed to you, means just go to that direct folder, and either you can open a command prompt from here, going to extensions and open a new command prompt, open a command prompt from here, or you can click on this icon and you can open up command prompt here, and from there I showed you how I copied that .zip file from my local directory to wherever this CentOS is installed on the system. So now, so pre-process, as I discussed with you, you can run the project, or you can first pre-process the project. So here, projects pre-process. So let me see if I have. So when you pre-process, so as I said, instead of, so let me just first show you this file. So this is just a structure of an S-device file where I'm just trying to focus on this portion only. So instead of using, so this is an input file which is going to the S-device tool. So instead of giving a hard-coded name to the input file, we are using some references, reference names which when pre-processed will be means this thing will be replaced by some name that node specific naming will be given, and that now I'm going to show you here. So for example, this is the input file, TDR file, which is in the for example in sdevice command file. So when you pre-process that sdevice tool, or then that this at the rate TDR at the rate will be replaced by that node specific TDR file. For example, what I'm saying is, for example, this is your sdevice tool and this is your node. So this is your real node where the simulation will be run. So when I pre-process, in that case, for this, for example, node number 10. So I already have a command file related to node number 10 where this input file is for example in the form of this reference name. So when I pre-process it, that will change to n10 underscore message.tdr. So this is how pre-processing means. I will be using means what I'm discussing with you is this means for this command file I have not used some hard-coded names. I have used these reference names. But when I will pre-process that node, then that name will change in this fashion, means that node specific name and that name will be given. For example, n10 underscore message.tdr. So this is how during pre-processing these references are replaced by this node file names specific to that node. So now this is regarding indexing, means how to index means or how to reference a node. So here I will just try to explain you. So hello, Sushant. Hello. Is anybody Sankalp?
Yeah, tell me, Naren.
So yeah, so when can we means take break, means can we have it?
I think you can take now, maybe
Yeah,
for
because
10 minutes,
yeah,
like 1.5.
yeah. So to the participants,
Yes, sir.
so
Hello,
sir,
Prince.
hello.
Yeah, we can schedule sir break for 10 to 15 minutes. No issue.
10 minutes. Oh, you want 15 minutes? Okay. Prince, you want to give a break for 15 minutes?
Yes, sir. We can schedule break 10 to 15 minutes. No issue, sir.
Okay, Naren, then yeah, we can take a break now.
Yeah.
It's
So
11 o'clock, right? So maybe
yeah.
we meet at 11:15.
Okay.
Yeah,
Sir.
sure, sir.
Yeah,
So
we'll meet
yeah.
at 11:15 then.
Yeah. Okay. Then we will again resume from here at 11:15. Okay.
Yeah. Okay.
Hello. Yeah, yes, Samir. Yeah, actually, means Sushant said that there is a lag in screen, means whenever I'm changing the screens now, it I'm at home. Sorry, I'm in office,
Yes, sir. There is a small little bit.
so I'm going a bit slow.
Yeah.
Yeah. Okay. Oh, okay. Thanks. Hello. Ah, okay, sorry. Okay, okay, sorry.
Hello, Prince, sir. Hello. Hello. Hello, Prince sir. Hello. Hello, Prince sir.
Hello,
Hello. Is it Prince sir?
Narendra, can
sir. You are co-host now. You can present.
Narendra, you can present now. Narendra, can you hear?
Narendra sir is mute, sir.
He's joining. He's joining.
Yeah, I'm joining. Yeah. Hello.
Hello. Yes, sir, you are audible, sir.
Yeah. Okay. Thank you.
Naren, you can click enable editing on top. Then you can go to preview full screen.
Yeah.
On top, enable editing.
Enable editing. Screen. Then.
No, you have to share your other screen.
Which. So my PPT is visible.
Yes, sir, it is visible. Can you make it full screen?
Yeah. So Sushant, we are okay.
No, it's not okay. It's not full screen right now.
So no. So I'm. I say it's not full screen. You're saying.
Yeah.
Okay. Just a minute. So now, should I means I'm entering to slideshow view. Okay.
Please do that.
Okay.
Now you do one thing. Now you are sharing your other screen actually. Do you have two monitors? Narendra, can you hear?
Yeah, I can hear you. Means.
But I asked, do you have two monitors?
Yeah. Yes.
Are you sharing only one screen or two screens?
Okay. So. Okay. Now. So.
No, what I'm saying, are you sharing both of your screen or only one screen?
So I think you are seeing two monitors, na? Now is it fine? Just a minute.
Yeah.
Okay.
Now present.
Oh, yeah. So,
Go.
yeah.
Now go full screen. Yeah, all good. And you press Control L. Yeah, good.
Yeah. Now
Continue
it's
now.
fine, sir.
So, okay. So we had stopped here before we went for break. Am I clear?
Clear. You're audible,
Okay.
Narendra. Continue, please. Yeah.
Yeah. So now, so as we were discussing, we do not use hard-coded input files for the means since we need to reference various nodes means we need to so that their inputs can be included in our present simulation nodes. So how are these nodes referenced? Various nodes. If suppose you are, for example, this node 65 is your current node means here, and you have written some SVisual. This is inspect, but you have written some SVisual script for this node, and you want to access data from other nodes. So how is this node referencing done here? So this at node at will reference to your present node wherever you are means now I'm particularly discussing this horizontal orientation of our project. In this horizontal flow, this this straight line refers to this horizontal direction means, for example, when I say node -1, then this -1 is referring means previous node with respect to our present node. So this will refer to node 53. So as it's means here it's written. So even previous, if you are here and if in your, for example, if you are at node 65 and for the input file specific to node 65, if you have included the syntax something like this previous, then it will fetch data from this node. It will refer to this node. Then in the same in the same column, if you want to access other nodes as well, so instead of this means vertical line, you will be using a column. So you can now in the same column. So for if it's -1, then you go one level up, and if you say node colon some plus value +1 +2, then you go levels down. So this is how you access or reference nodes within the same column and at the same level or in the same horizontal or at the same horizontal level, you use this vertical line to access this. This is for this horizontal structure of our project. Now, so when we write means at the rate node 2 label, then we do not have to give this reference in terms of this like this numbering. We can directly, for example, if I am here and I want to access this tool or I want to access this SDE tool, I can directly write node this label of this tool. Then it will directly fetch, it will directly refer to that particular node. So these are some of the ways where in which you can reference other nodes from your present node. So here I have included one example. So let me just a minute. I hope now that this lag is a little bit less. So this my SWB, I hope my SWB screen is visible.
Yes, Naren,
Now,
it is
now
visible.
I have included this simple example script. So, for example, so just, give me a minute. So basically, what I'm trying to explain is that means so actually, so if some projects, so this project is I had created this project. So if I am at node 98, for example, and and this is related to some SVisual tool. Now, for this SVisual in this is my SVisual command file looks something like this. This one. For different nodes, the node specific copies of that command file will be generated. Now, if I am at node 98, now for node 98, when I pre-process this, so how does after pre-processing, how does this pre-processed file look like? So after pre-processing, so for node 98, my node will be changed to 98. Now, for previous, so for this node, previous in the horizontal direction is this node 12. So you will see this is as node 12. Now, for in the horizontal direction at -1, so I am at 98. Again, when means I am writing -1, then I am just referring to this one level to the left on the horizontal direction. So again, it's 12 only. So this previous and node -1 are acting same. Now, if I want to go first one level left and then 2 levels down, then I reference that node in this way. -1 colon +2. So I go to node number 78. Now, if for that particular level, left level, I want to access all the nodes in that column, then I write it like this. So I can access all these nodes, 34, 12, 56, 78. So it's here. Now, if I want to refer to which experiment this node actually belongs, so it belongs to this second experiment. So this. Does it belong to multiple experiments? No. So it's again showing it only belongs to second experiment, this particular node number 98. So what's the tool level for this particular node? So it shows me this is S visual process, pre-process. This is the tool level which is given. And what's the present working, the working directory for this, or where is this node located? So it's located here in this directory. And which is the TDR file this particular node is referring to? So it's referring to this N FPS, this one, related to this TDR, whatever TDR file generated from the S process. So this is a simple example of how node referencing is done in this S visual scripting. Now, okay. So here are some more things here. So I have defined some variables. This SW variables, then simple tickle variables. So if you see this, only this tickle variable is means only this syntax is visible over here. Means this variable you can see, but this rest, these two variables you can't see in this pre-processed file. So this setH, the variable which was using which was set using this hash setH, that you can see in your output table, CentOS table on the means in that table this means variable is getting printed. But what about this variable which has been set using setH? So this is a hidden variable. So it is not neither showing in this preprocessed file nor in the output table file. So but we can, for that particular node, we can see whatever variables means have been defined for that node. So we just click that particular node, go to Node Explorer. Let me show you how. For example, for any particular node, just click that node, then go to Node Explorer, and then go to Node Data. And so here you can see the various variables. So this is what I'm trying to show over there. This hidden variable which I had defined, that you can see over there. So this variable 1, you can see it here. So it's again referring to that present node number 98, which I'm referring to. So this is a simple example of node referencing in this SVG scripting. This I already discussed in how instead of using hard-coded input file names, we are just using reference file names, so that for each node that file name will be converted in this fashion. Node n and node number underscore extension of that particular tool, whichever tool we are referring to, and then file extension. And this again referencing is similar as I showed you for node. So again, for the present node TDR file, then TDR file for the previous node on the same level in the left direction. So node referencing is in the similar fashion as I had used node instead of it, means this referencing is the same. This is a just simple example of how this means. For example, this is my input node where I am giving some input files, some output files. Then after pre-processing, how these names will be replaced by for that particular node. These node files will be generated. This is just an example of referencing. So adding parameters. So how do we add parameters? Means, for example, if you see here, when the example which I'm showing you, here I have 4 experiments over there, and and here I have 1 experiment. So if I want to include more experiments, then how should I do that? For example, in this experiment, after creating the structure in the S process tool, then I am doing this simulation, edge device simulation to get electrical characteristics. So for example, I am doing this for single value of this VD-lin parameter. So what if I want to do this for multiple values of VD-lin? So you can just either you go from here. For example, either you can directly add from here parameter values. For example, for this parameter VD-lin, you just enter values. For example, let's say 0.05, 0.1 or 0.15, for example. So this a linear list I'm defining, then just clicking on apply. So you can see now I have 3 experiments. So I means using this VD-lin parameter, I was able to create, I am just varying the value of parameters and I'm just creating multiple experiments from like this. So now you can see the device behavior, how or IV characteristics for different bias ranges. In this fashion, these are the parameter level, different parameter levels. So you can just go on adding parameter values and creating splits in the experiments, and you can create multiple experiments like this. So this is how you add parameters and you create multiple experiments. So these were the things I needed to discuss. I wanted to discuss regarding SWB. Now, as I said, let's look a little deeper. Let's discuss more on SVisual. CentOS Visual is our visualizing tool for various CentOS TCAD tools, from where we generate TDR files or XY plots. So this will just looks few of these things. What we in the SVisual. So yeah, this I already discussed with you. For example, for this edge device tool, this is our this one is my real node, which was for where the simulation was run. So till this point, now my simulation is done using SVisual, and I had used using S device, and I used SVisual tools to just view the outputs. So as I have said you that when we select this node, then we can visualize using these 3 options. This already I discussed with you. So now once you are in the so for example, now I was in the VD here. I was here. So for example, I want to quickly visualize whatever simulations means outputs are there. So for example, let's visualize. So once your SVisual window opens, it looks something like this, whatever you're seeing on your screen. So this is your data selection window. So when we simulate a device structure using S device, then for that structure, different types of fields are simulated, or the output is generated. For example, doping concentration, electric field, electrostatic potential. These things can right now. Right now, this structure is showing you the doping concentration field, but so you can see just you can check check and uncheck various fields, and you can see different data within this structure. So this this is your data selection field. Once you have selected some structure, then you can do manipulations to change the this rendering of this, or how it looks, by going into plot properties. So this is the thing which I was showing you, data selection window. So these are the means in the structure file. So this I already explained. You select the node, then click on yes visualize, then it. So we saw that it by default opens in means opens this net active concentration or doping concentration. So for this structure, we can choose what we want to show, what we do not want to show. Means from if we check and uncheck. For example, if I do not want to show any regions for this, so these regions have gone. So what we want to show in this window, what or means those we can check and uncheck from here. So this is how we can turn off, turn on various whatever things we want to see or we don't want to see. We'll see how we can take cut lines and maximize plots. This figure I had shown you means, so for example, in my file, when just a minute. So for example, in my this ID visual and S visual thing. So for this, I can directly open using this run visualizer icon. So for this tool, I have written a command like okay. So current tendency, sorry. So for this S visual tool, the command file is written like this, that it directly plots this thing. This is what I'm showing you over here. So this structure is generated. Then we can, as I said, we can change how the things looks for us. When, for example, in the doping concentration, by default, so this is showing me contour filled plots. So by default, this coloring scheme, which is referring to the doping concentration. For example, this red is showing means largest means highest N type doping concentration. Then this dark blue is showing me the largest P type doping concentration. So by default, this these levels for which we have defined various coloring sequences. So by default, 31 levels are defined. Means to say that going from -517 to plus 520 plus 520, I'm going through by default 31, but I can change that. So if instead of 31 levels, I'm just using 7 levels of this doping concentration. So this is how it looks. So you can see that when I'm using larger number of levels, then this is very fine. This gradation is very fine in coloring, and it's coarser when I'm using a lesser number of levels. Similarly, means we can overlay the structures. For example, so let me close this. So for this ID visually, if I open again, visualize quickly. So it's actually, so go to Windows, then restore all, then maximize. So if I want to overlay, for example, 2 plots, so you can select Shift plus click. Then for example, I have selected these two plots. Then I can overlay these plots. So this is the overlaid plot. So now I can change the means whatever data field I want to see, or whatever other things which we have seen in data selection section. So for example, now in this overlay, now we will be able to select manually for each device. So for example, for this device, I can choose the various data. Since I have overlaid 2 different structures, I am able to specifically choose them, and then I can choose whatever fields I want to show over the structures. Then just means wanting to say that we can overlay different structures and we can compare different fields in that. So here So this here is just a simple contour lines means the two structures have been just overlaid and contour lines have been drawn for them. So just structure overlaying there. Then how to take cut lines. So if, for example, you have a structure and then you want to see, for example, you want to draw a band diagram for the structure, then how to do that? So for example, let me take this structure and maximize it. So for this structure, if I want to see a band diagram in this direction, then I will do a cut line, a Y cut line. So let's select Y, do a cut line. So by default, it's opening this. So I mean, since I had chosen initially this electric field, but we have a ready-made tool, means this tool, we can directly means create band diagram for this. So see, means after creating the cut line, I can directly draw the band diagram. So this is one more feature of SVisual that you can directly take cut lines. So you can take cut lines for 2D structures, 3D structures. But this band diagram, for example, this XY plots will only be drawn when you have, for example, you have for a 3D device, you have narrowed down your view up to 1D by taking this plane cut lines. So this only then this XY plots will be generated for this 1D structures only. So this is again now means here I'm showing you this linking. So I have linked these two structures. Then I have taken the cut line, so I can now see the band diagrams simultaneously for the two. So the structure is the same, but the band diagram which I'm showing over here is for different biases. This is under equilibrium bias. This is for positive bias at this topmost or gate terminal. This is the same. This is the same cut line, but there instead of showing you the band diagram, I am showing you the electrostatic potential. Again, this red one is for equilibrium. And after I apply plus 2 volt at the gate, so this you can see this potential is just plus VG. So it has shifted by 2 volts up after.
Sir, your screen disappears that you shared now had gone.
Sorry for that.
It's not visible.
Sorry for that. Is it?
Yeah.
I think it's appearing now.
Yeah, now it is appearing. Yes.
Okay.
Yes, sir. Please continue.
Okay, thank you. So I think means we were here means linking two structures, then taking the cut line. So means this cut line will. So I can now I can simultaneously show you cut lines for these two structures. I was showing means band diagram at different, one for equilibrium bias and one for positive 2 volts. So corresponding to this band diagram, I showed you this electrostatic potential with this at 0 when 0 volt is applied, this when plus 2 volt is applied. Then you can also change the how your window looks like. SVisual window means settings you can change by going into the edit preferences. Then, for example, within the preferences, for example, what should be my scripting language use? So by default, it means for here it's TCL, but you can also use Python-based scripting. So this, from here you can change whatever preferences you want, how your SVisual window should look like. So this is, for example, when I'm using Tickle, then this icon actually shows this difference. You will see this icon is for Python. So in SVisual, for example, whatever SVisual I'm showing you, you can see here in this prompt. The prompt is this percentage sign. This is for Tickle. But if we change it to in Python mode, then your prompt will change to this 3 greater than triangles. So now, this is a coordinate system. So the structures which I have been showing to you, in which this the structures in here, your downward direction is pointing in the your x direction is in the downward direction, and this horizontal is your y direction. So this is your universal coordinate specification, UCS coordinate system. This is what I was saying. In UCS, we have x-axis downwards, y-axis horizontal. So in this, I was showing you the whatever TDR files. It was in UCS coordinate system. Now, as I said, you can just see means you can switch off the field values. You can just show the regions, or you can even just show the boundaries. What I was referring initially. So you can just check and uncheck these things. Whatever you want to see, you don't want to see. If you want to see regions, no means. So for example, you want to see bulk regions, or you want to see fields. If you want to switch off the fields, it will be switch off. Only you will see the regions. So this is how you can switch on and off what you want to see. For example, in this structure, the grid is on. So if I switch on the grid, you will see the grid. So anyway, means this grid are the means meshing. This is generated after meshing. So means these are the grid points are the where we solve our numerical equations. We'll talk about this when we will discuss edge device later in other sessions. Now, so different regions, as I said, you can check and uncheck in that window if what regions you want to see, you do not want to see. So whatever materials are defined within the center environment, they are listed here. You can see the material list over here. You can even show means interfaces, or you can even show contacts. This you can means you can show means on and off by going into particles. So through these particles, or so basically you can just you want to show or not this interface. Basically, you just for this eye icon you check and uncheck, and whatever you want to see, you don't want to see. Then regarding this coloring scheme. So as I said, means this meshing means these are your triangular meshes. So and data is defined over these node points, and this interpolation, or this, for example, color interpolation, how to go from blue to yellow. So this coloring interpolation happens over this mesh element. This is how means your coloring means you are referring to the doping, but in using some coloring scheme, then how this coloring scheme is getting generated from node to node. So how this interpolation is being done. Then so as I said, means interpolation is being done. This coloring scheme interpolation is done between two nodes over the mesh element color. And this color, as I said, as we have been discussing, these color contours are used to represent data elements. And this for contour field thing, contour field plots, we are defining for some data range. So as I said, by default we are using 31 levels. For example, from going from p-type doping to n-type doping, we just use 31 levels. And so for these levels, and for going from this doping to this doping, from, for example, from p-type doping to n-type doping. So for a band of values, for a range of values, a single color is defined. So color, and then that range goes on changing. So this is how this color is being filled within this area. Now I will quickly show we already saw this graph. Means, for example, I have defined a S visual tool just to show the plot, ID visual in plot. So when I just click on run visualizer node, so it will directly open that plot for me. So it is directly opening this plot for me, gate voltage versus this drain current. But this is how I have actually scripted. Means, so if I try to open this again ID visual lane by from this as visual window, for example, I go to quickly visualize, and so let me open that window. So yes, let me first close this. So if I select the node, I go to visualize. So you see, as I said, means for IV plot, it's showing me a blank frame. So first I will maximize this. I will select it, click on maximize. Then if I want to generate IDVG, so I will select this data set n10_ds. This is the data set corresponding to that node, which is containing my IV data. So I will select gate. I will, for example, gate's inner voltage, I will plot on X. Then for the drain, I will select total current. I will plot it on Y. So now what did I will do wrong? So let me just first delete this. So means for this data set, if I get, for example, gate roll X, then drain total current. So maybe I might be in the wrong node then, if it's not showing IDV. So this might be then IDVD. So basically trying to IDVG lane. So basically trying to say that means
Naren, you need to plot the gate voltage against drain current, right?
yeah, so that's what I was.
And did you select the right PLT file? Select the one on the top, IDVG underscore and.
Sorry, yeah. So yeah, correct.
Yeah.
Thank you, Samir. So let me first delete this plot. So actually I was using wrong data set. So we needed to see IDVG in. So we need to first open, select that data set, then select gate voltage and let's plot inner voltage on x-axis, then drain current on y-axis. So this is how, now this is in linear scale then. So if I plot on log scale, this is the graph I was showing you. Now this I have now generated this manually, but now I need to set various properties for this. For example, I want to change this line thickness, then I go to shapes, then I increase the thickness. So this is how, so this, you see this, I am doing this manually, means I have, first I need to select the correct data set, then I need to define the dependent and independent and dependent variables and assign them to axis, x-axis, y-axis. Then after generating the plots, I need to then change the settings, what means. So that these things can be automized. So this is time consuming, then it can be automized in S Visual Script, and that is what that was done in this file. For example, if we open this file, so whatever I'm doing it manually, so that can be scripted. Samir will discuss in detail about the scripting, so that once when we directly run this, we get we get our output in desired form which we want. We can means automate that thing instead of doing everything manually. So this is the script I was showing you. This is no. So this is the visual script I just showed you in the previously. Now these are the things I wanted to discuss regarding as visual. Now again means I had shown you means what are the different online help available for you if you want to means practice means CentOS TCAD by on your own. So as I said, you can just go to this training. So from here, you can search means different examples, means application-based examples, then and how to search them. For example, so right now means we are here as I showed you. So this functionality means allows you to means navigate through various projects, and these projects are defined. Means we already saw that they are under our applications library. We saw it in SWB window. So when you click on this application area based search, so you see like this. So these are your projects. Means SW means application area wise means this sort, and these projects are sorted depending on application areas. You can just means just navigate through them. So these are the means various command files. Means you can go to them. You can see inside them. So this is the online help means depending means application area dependent projects. You can see. Then you can see search the PDF files, documentation. So for example, if I go again search here, go to search documentation. So you can type any keyword here, and you can, if you enter, you will get means related to that keyword. You will documentation will pop up like this. For example, if you enter CMOS, and then there are different, you will get different links, and you can just go through them, and you will see the related documentation for that project. Then the last option is means one more option is there that you can just so you can just search the various command files. So you just type one command, and whatever command files are there in various projects, that a list will appear for you. A list will appear, and from there you can just go to that particular command file and you just see the command file. So these are the different things which I wanted to discuss regarding SWB and SVisual, and these are the various sources which, if you want to learn by yourself, means practice by yourself, then these are the various sources you can refer to. Now I will hand over to Samir. He will take you through this scripting part which I was discussing initially. Thank you. Hello.
Hello.
Yeah, am I audible?
Yes, sir, you are audible.
So
Hello. Yeah, thanks, Narendra. So, Prince sir, should we give one more break, 5-10 minutes, or should I continue?
Yes, sir, we can schedule. No issues.
Pardon?
We can schedule, sir.
Okay, so then another 15 minutes, so 10 minutes maybe. So 12:15, let us meet. It's 12:04 right
Sure.
now. Okay,
Sure, sir.
thank you. Hello.
Yes, sir, you're audible, sir.
Yeah, is my screen visible?
Yes, sir, you can start.
Okay. Yeah. Hi. So I'm Samir Shah, and I'll be talking about tickle scripting for CentOS Visual specifically. So earlier, Narendra showed us how to work with CentOS Visual interactively, and he also pointed out that all those, all the commands, the corresponding commands are echoed in the CentOS Visual command panel or command window. So what that means, what those commands mean, that's what we'll have a brief look at. So I'll provide an introduction to a brief again overview of CentOS Visual and Tickle scripting. This is tool command language, so it's abbreviated as Tickle, TCL. So we'll see the basics of Tickle and then CentOS Visual commands basically, and then extraction library for extracting parameters. And actually I have a lot of material, but I'll skim through some of the slides. So many of the materials that we have in these slides are covered in this tool command language. So wherever I feel that material is readily available in this tool command language tutorial, I'll skip those slides. And so I request all of you after this tutorial to, after this workshop, to go through this TCAD CentOS tutorial. Naren already told you how to access it, right? So you can go through CentOS Visual tool command language. So this is pure Tickle, and of course CentOS Visual can be used in both Tickle and Python mode. So we have a Python tutorial as well as a tool command language TCAD tutorial. So yeah. So yeah, so this diagram you will see again and again. Once Sushant will show you probably, and Narendra will also show you probably. So we have this tool flow. He showed already that, Narendra already showed us that we have so many TCAD tools, and then to perform a particular simulation, we have this sort of tool flow, right? We need to select the tools that we want, and in the simulation tool flow, tomorrow you'll be building a structure using S process, NMOS FET structure. And then of course we carry out the device simulation using CentOS device, and CentOS Visual is a tool for performing, for visualizing the internal data, right? We can look into the structure and understand the device operation. So for example, here I'm visualizing the electrostatic potential. Again, Narendra has shown so many of these plots. I can visualize the terminal characteristics. For example, this is the drain current versus gate voltage plot of a MOSFET. And then of course we can extract the device parameters. So you see here, I'm extracting all this IDSAT and IOF and threshold voltage, subthreshold slope, transconductance. So yeah, all these parameters can be extracted in SVisual. So yeah, again, CentOS Visual is a data visualization tool for XY plots. Formally it is 1D plots, but yeah. So 2D plot and 3D plots in which we see the structures, we can perform, and basically it's for TCAD tools. The data comes from TCAD tools, and then it can perform data processing. We can manipulate the data and then come up with the plots that we desire. And then of course we can extract parameters. We can work interactively with the TCAD data as shown by Narendra. And then of course we can automate tasks with Tickle based or Python based scripting. So that's what I'll be focusing on, Tickle. So I'm not going to cover Python in this, but yeah, you are welcome to go through the Python tutorial. And the concepts apply to both Tickle and Python based SVisual. So basically, so I'll be focusing on this Tickle basically today. And as I said, Tickle is a tool command language. It's an interpret language, and it allows us to add tool specific commands. So that's what SVisual does. So we have Tickle, then SVisual Tickle. So we have Tickle commands, and then we have SVisual Tickle commands. And Tickle is used in many of the Synopsys TCAD tools like CentOS process. So tomorrow, Sushant is going to talk about CentOS process. So those are all the command file he'll show you, and those are all Tickle commands basically. And more specifically, they are CentOS process Tickle commands. So any of these tools, we can use all the core and of course CentOS Visual. So we can use in both of these the core Tickle commands, on top of which we can use the tool specific tickle commands. So this is the, yeah, so tomorrow S process, S device, yeah, again it will be covered tomorrow and after tomorrow. So once we simulate the structure, it generates these TDR files. And of course, we can also visualize 1D profiles using PLX files. So we can store data in 1D profiles in PLX files. So that's what is visualized. That's what is the input for CentOS Visual. So all this TCAD data as well as a command file. So the command file operates on the TCAD data, and then it produces the result that we want basically. So the inputs are basically, as I said, S process structure, and then TDR file which is generated from CentOS device. So that contains all the field data like electrostatic potential, electron density, hole density, currents. So many of these can be created in CentOS device, and they can be visualized in SVisual. And then of course the terminal characteristics are saved in this underscore des.plt. So even that is loaded in SVisual, and that's what Narendra had shown earlier. So this TDR file, we can save both scalar data and vector data. So they are called formally field data because they are defined at all points, all the grid points inside the device. So yeah. And of course, the output of CentOS Visual is simulation log files. And then, so that just shows the output of running the SVisual command, SVisual script. And then we can save the data in CSV file, and then you can take it to Excel for further processing. And I can also create images. I mean, whatever plots I have created in SVisual, I can create images and then insert them in PowerPoint presentations. And I can also create movies in SVisual. So yeah, there are two execution modes of CentOS Visual broadly, and one is the batch mode and one is interactive mode. So batch mode is the default, and the command, if I open a Unix terminal and I want to run a SVisual command script file, then I'll say SVisual -b for batch mode, and then .tickle, whatever the file name .tickle. And for Python, it will be .py. And in interactive mode, I'll just say SVisual and then tickle or Python script file over here. So the batch mode, the GUI doesn't open up like this. And we just carry, I mean, mainly it is done for extraction purpose. So to extract all these parameters, or even to create the image files or create movies, those are done in usually batch mode. So most of the application library projects, you will see that SVisual is run in the batch mode over there, although you can visualize the curves also by running them in interactive mode. And then, yeah, so interactive mode means it just opens up the SVisual window. And of course, there's a third mode called CentOS run visualizer nodes together. So that runs the visualizer on multiple nodes, and Narendra has already shown you that. So that just opens the SVisual in interactive mode. Yeah, so these are the out files and error files generated. So any errors, out file has the printout of running the SVisual tickle file. And then this error file contains, if there are any errors, this node will turn red, and then the error messages you can read in this error file. So there are different plot types. This is just a summary. So 1D plots or XY plots, these are different types of XY plots which can be generated. 1D doping profiles, and then I think Narendra showed a lot of 2D doping profiles. So then IDVG terminal characteristics, and then 2D and 3D plots, scalar field plots and vector field plots are generated, can be created basically. So if you load a structure, by default, it will plot the default scalar field, which is either net active or in case of S process, or doping concentration in case of S device. And so the scalar field is plotted, and of course here I'm showing so you can choose any field which you want to plot, and I'm showing electrostatic potential over here. And we can also create vector plots. So on top of electrostatic potential, I can plot the electric field. So this is at high voltage. There's a contact here, anode and cathode. This is a simple resistor. So this is at high voltage, and this is at low voltage this end. And this shows the electric field or the current plots or the current density vectors. So here the electric field is pointing from high to low potential as expected. And yeah, and the current is flowing from high to low potential basically. And of course, we can take cut lines and create this band diagrams also. So yeah, I'm not going to discuss this. So these other plots you can readily get from the manual how to create them. But then even this band diagram, in the manual, you can see how to create these different plots. I'll discuss this electrostatic, how to create a scalar field plot. And then even this band diagram, you can see in this particular application library example, solar cells, there's a script for creating these band diagrams. And yeah, so yeah, here again, I'm showing this. I think Narendra already showed this. I'm plotting this total current density as a scalar field as well as a vector field over here. You can see the direction of currents from drain to source over here. And so basically, I'll be focusing on this tickle console panel, which you can turn on and off using this button over here, which says tickle. And in case of Python, it will be Python over here. And so if this is selected, then you can see the tickle console. In case of Python, it will be Python console over here. So you can differentiate between the two basically. So this % is the tickle prompt basically, and in case of Python, it will be 3 greater than symbols over here. And as you can see, these commands are getting executed whenever we do things interactively over here in this window. And I'll show you an easy way to create this tickle script, visual tickle script files. So we can just perform the operations that we want and click on this save button. So essentially the command history is saved in a tickle file, can be saved in a file basically. So we do whatever we want in this plot with all these buttons. And then finally all these commands are getting echoed over here, and then we click on the save button, and then we can save it in whatever script we want basically, those commands. And then of course we need to edit those files. So some basics about SVisual, tickle, and then of course how to create plots interactively. So this is a typical command file, tickle, or this is SVisual tickle, and so this will run with any tickle interpreter. You don't need SVisual tickle to run this pure tickle file basically. So as I said earlier, SVisual tickle is built on top of tickle. So there are many components here. You can see these are the SWB preprocessor command, which already Narendra spoke about. And then you have these SWB add references. And then of course this is tickle command, pure tickle command is set and if, and of course this set, and then load file is a SVisual tickle command. So essentially a command file is a combination of all these elements like tickle and then SWB preprocessor commands, tickle commands, and then Cetorus tickle commands, and of course this tickle extraction library command. So these, from this part, I'm using this tickle extraction library commands. So you can see they are preceded by ext or lib. Yeah, and so if you look at this structure, you can of the command file over here or here, you can make out that okay. So we separate this, each line is a, each group of, this is a tickle command basically, and we separate the tickle command by new lines, right, by pressing enter over here, and then a new line gets created. Or we can also, if we want, we can separate, write everything on a single line. Of course, it doesn't look very pleasing, but yeah, we can separate these by semicolons, all these commands, and then yeah, even that is possible. And tickle commands are case sensitive. So basically set, you see, right, you can't have capital S over here and capital P or PU, yeah, or capital PUTS, yeah. And of course, the standard extension for tickle command will be TCL file extension. And then if you are using SVisual through the through SWB, then the standard extension of file name is _viz.tickle. And for Python, it will be .py, and here it will be _viz.py. So yeah, so we can also continue. If the command is long, then we can continue on the next line using this line continuation symbol. You see a backslash over here. So the backslash character is used to continue the same command on the next line also. And you can also use comments throughout the script. So hash is a comment character. And you can also have, so all the characters after this hash, they are treated as a comment. They won't be executed by the tickle interpreter. And so we can have a comment on its own line, or we can even have a comment in line. That means there's a command here followed by a comment. So we are separating it by semicolon, and then we are putting a hash over here. So all the characters after this hash are treated as a comment line. So this is one command, and then this is another command. So we are separating them by the semicolon basically. And a tickle script, it can be loaded into another tickle script. So I can source, I mean, let us say I create a library of tickle commands and save it in a file. I can source it in the tickle, SVisual tickle or tickle interpreter using source command and the file name .tickle. So yeah, so what is the typical structure of a tickle command, and what are the command options that are used? So basically a tickle command, it consists of multiple words and they are separated by spaces of words. So for example, let us consider the set command over here. It is used to define variables. So this first word, so it has 3 words because you can see there are 2 spaces over here. So there are 3 words in the command, and the set command is the name. So first word is the name of the command, and all these others remaining words are treated as arguments to the set command or to the command name. And we can also have command options. So you see this puts. The puts command is used to print a string to the console or to the, yeah. So then we can have this. So this is the documentation from standard tickle manual, which is available online. So you can see these are the options basically. So they modify, basically they modify how these commands operate. So yeah, so all these are arguments, and then arguments are nothing but inputs basically, which are provided to the command. More formally, a command is a procedure. So yeah, so and in other programming language, they are called functions also. So these are defined by tickle basically. They are inbuilt into any tickle interpreter, whether it is SVisual or not. And here the order of the arguments is fixed. For example, in tickle, basically, if you're tickle, you have fixed order, set x1, then expression, this is an expression command for computing a value twice, 2 times x. So yeah, this order is fixed. But then, and sometimes we want flexibility. I mean, for especially command having many arguments or many inputs. So I'll show you next how to do that. I mean, how SVisual tickle does that. And all commands, all tickle commands return a result. So for example, here set x1, we are creating a variable x, and it has the value 1. So that value is returned by this set command. When tickle executes this command or runs this command, 1 is returned. Same thing for the expression command. So I'm multiplying this value of x by 2. So then that is the return value of this expression command basically, which is 2. So this was the command structure for, I mean, the syntax for the pure tickle commands. And now if we go to center of visual tickle commands, we need flexible syntax basically. So we need to specify the arguments or the inputs in arbitrary order, because there could be many arguments for a typical center of visual command. And then we need to be able to flexibly specify them. Many of them will have default values. So I don't want to, let us say there are 10 arguments and 5 of them, I want to use the default values. In that case, I need to be able to change the order in which I'm specifying these arguments or inputs. So for that, CentOS Visual tickle commands have been implemented in such a way that you have this command name. Of course, the first word is always the command name, whether it is tickle or SVisual tickle. And then that is as usual followed by the arguments. And then you have this keyword value syntax. So because of this, you can have a dash over here and then specify the keyword and then the value. For example, here I'm specifying the file name because that's what I want to load using load file command. And then this dash name is the keyword here, name is the keyword here, and then the value is plt lin. So basically I'm loading a file and then saving the contents of this plt file into a data set. All the values are getting stored in this data set. So that's what this means. So I can change the order basically. That's the whole point of having these this dash syntax basically. And so on top of that, of course, CentOS Visual. We have this extraction library procedures also, which have been implemented and as part of SVisual, and then they are preceded by this ext : syntax, procedure name, and then again keyword value syntax is there. So yeah, so just to summarize, the arguments are saved as keyword value syntax. So that's what I mean by this sentence over here. Yeah, so if you need help on any tickle procedure, this is online manual pages are there. So the current version in V2403 release of SVisual is 8.6, and so you can refer to the online documentation. For example, here is the online documentation of the puts command, and then so this tells you then what it does, right? This puts command, it writes to a channel. So channel here is the name generally either to the terminal or to a file. So that is more generally referred to as a channel. And then of course this puts command has these options, no new line. So by default puts will print a new line after printing the string. So if we want, we can, if you don't want puts to print a new line after printing the string, then we can have this no new line option. And then we can control where we are printing it, either to the terminal or a file using this channel ID. So, and here, so here is a brief description of the command, and then in many cases you'll have so many. So this is followed by, after description, you will have the arguments and what they mean. Basically, I didn't print it out over here. So that was about Tickle help, how you can get online help from Tickle, and then for center as usual, you can simply type this help. You can simply ask for help here, like using the help command. Okay, so these are as usual Tickle command basically, and then we say help and then command name. So help load file will give you a printout of what it means, basically load file. And then extraction library also you can take help basically. So you need to load the extraction library first using this load library, and then you can ask for help. So you put the name of the extraction library and then help keyword and then the value of 1. So this way the help message will be printed, and then there are examples also. So again, the purpose of the command, the syntax, the arguments, and the examples, everything is there readily available for you basically. So yeah, I've already explained puts. You print out a string. We enclose strings in double quotes. So here we are printing puts hello world. So here I'm just starting a Tickle interpreter using TCAD such command, and it's printing in the terminal this hello world string. And if I don't want to print a new line, so you see right after this, there'll be another %sign over here. But then if you do say no new line, if you use this option, then you can see that it is printed over here, and the command is starting after the word D character. So these are the ways you can control the output. And this puts can be combined with the format command, which helps a lot in printing values the way we want basically. And of course, there is a center of usual Tickle command. So what happens is if you, while doing the interactive work, you can use echo, because in interactive mode, this puts will print to the terminal. It will not print inside the Tickle command window or the Tickle console. So if you want to print something inside the Tickle console, then you need to use the echo command. So which is as usual Tickle command. So yeah, this is just a comparison of puts and echo. So at different places I've used echo and puts. So yeah, so you see puts is used over here, and then puts output appears like this. But then if I'm using an echo command inside a script, and if I run it, then you can see it is preceded by the output of this echo command is preceded by this #tickle : #. And from here it will start printing whatever I'm asking it to print. So this there is subtle differences between these two echo and puts, the way they appear in the out file of SWB. So yeah, now I'll show a very simple way of creating scripts. So how can you create scripts interactively using command history? Because the thing is, we are, let us say we are visualizing things again and again. So every time you have to load the PLT file or TDR file and then manipulate the plot, and then and once you close this visual window, all those commands are lost. So you run another simulation. Let us say I run this particular row. I create the structure, I plot IDVG. So I simulate IDVG. And then of course I can load the PLT file interactively for this node, right? And then create the plots interactively as Narendra showed. But then once I close the visual window, it's gone. All that data is gone. All the scripts, all those commands are gone. So I have to again open n15_des.plt, execute the same sort of same command again and again, and then so that's a big waste of time. So it is better to create scripts and then have a SVisual node here in which it is doing all the job for you, so that you don't have to repeat those steps again and again. So what we do is we can start SVisual in interactive mode, and then we can create the plot interactively. So we create a basic script. I mean, this is one way of doing it, of course. We create a basic script by running SVisual in interactive mode, and then those commands are echoed in console. We save it in the command so automatically SVisual will save it in the command history, all those commands, and then we can save it using the save button, which I'll show. And then of course we need to clean up the script. There are a lot of things inside the script which we don't need actually. So, and then of course we can parameterize the script. That's what makes it more powerful, learning how to parameterize the script so that, so let us say I create a script for n14_des.plt file that will not work for n15. So I need to make certain changes. I need to parameterize the script so that it works for both idvg_n14_des.plt and idvg_n15_des.plt. So for both these rows or for both these nodes, the same script should work. So we need to make certain changes, and we can, so we need to parameterize the script. We can add these references, and we can add tickle variables. So already Naren, I think, showed you these at variables, which are specific to SWB, and they are pre-processed. Basically, they are SW pre-processed syntax. So just to summarize again, at TDR at means it refers to the TDR file which is created by S process or SDE and CentOS structure editor. And by the way, I'm using these acronyms. So CentOS process, S process, CentOS structure editor, SDE. We won't be covering SDE in this particular workshop. So we'll create the structure using only S process. And I use S device for CentOS device, and for CentOS visual, I'll use S visual as a short form. Like, so this add TDR add syntax is very helpful in parameterizing the device. So I'm referring to the previous node TDR file. If I am saying add TDR add TDR that at is the output of this IDVG. This creates IDVG will create a TDR file. So I can use that in my CentOS visual scripts. Or add plot add is a PLT file which is created by CentOS device. I can refer to it by using this add plot add. So yeah, and of course after parameterizing or even before parameterizing, I can create a default plot, right? And then I can make it more pleasing, or maybe I can make it more publication quality, or maybe I want to put it in a slide. So I can modify this plot to make it look more pleasing. And then of course there are many parts of the plot which can be modified. So I'll show you how to do this also. And then of course we can ultimately export the plot as an image file for inserting in our PowerPoint slides. And we can of course create animations also using this methodology. So I won't cover animation, but I'll point to an example of how to create animations. So yeah, so let me just, I'll just run through this in my, so I'm showing my DSS session. I mean the SWB right now. I hope everyone can see SWB right now. So this is one of the startup projects which you have received, but of course I deleted some nodes from it for the demo purpose. So everyone can see my SWB screen. Sushant, Naren, is someone there? Can you confirm?
Yes, sir. It is visible,
Okay.
sir.
Yes,
Okay, sure.
yes, sir.
Yes.
So what I can do is, so I'll give a demo of how to create a script interactively. So let us say this is my project right now. I've created a structure using process emulation. That's what you'll do tomorrow. I have done the linear. I've simulated the linear IDVG characteristics, the drain, the gate voltage versus drain current, which Narendra showed just now. So I can simply add SVisual tool, right? I can right click on this, and if I go to tools, and I can double click on this SVisual, and I can even change the name here. So I'm going to rename it to structure. Okay, and please notice that, okay, all tools which are added, they are added in batch mode by default. So I'll say okay over here. And then now I can right click. And then if I right click, then a command file is going to get created. It has this structure underscore vis.tcl. So tool label underscore tool name, short tool name, vis is for visual, short for SVisual. So structure tool label underscore tool prefix dot tickle. That's the file name over here. So right now you can see it's empty, right? I mean, so only this file. So now I can start as usual. Let us see. I'll first let us run it in interactive mode. So I changed the mode to interactive by double clicking. I double clicked on the structure icon, and then I got this menu tool properties for structure dialog box, a window, and then I say interactive, and then I say OK. So now I need to save the settings. Any changes we make to the SWE project, we need to save the settings over here. And then I'll click on this N17 node and I'll run it. So now SVisual should open up because it's in interactive mode. So you see SVisual is being run and there is no -b over here. So just to confirm. So it's SVisual and then there is no -b. That means it is going to run this N17 underscore tickle file, which is a pre-process tickle file. Of course, in this case, it is just empty, right? So it will just open up this. So now the purpose is to visualize, to create a 2D plot. So I'll go to this open and then, okay, or I can do it the other way also. Let us see. So I can go here to N7. Let me do it that way. So yeah, that way I don't have to change this basically. So I go to N7 and then I click on this eye icon to load a TDR file. So you see now a TDR file is loaded, which is, it has the name n7 underscore fps.tdr. Okay, so here you see the load file command and then the complete absolute path, Unix path, and then the file name. So n7 underscore fps.tdr is what I loaded. And then create plot command, it created the 2D plot using this create plot command, and then it selected the plot. So in case of multiple plots, we need to be careful about which plot we are working in. I could have multiple plots here, so that is why by default it runs the select plots command, and it is selecting the current plot. The current plot has the name plot underscore n7 underscore fps. So all this is done by SVisual by default. That's what even Narendra had shown earlier, right? So it created this data set. Okay, I'll get into this later. So right now, just this plot name is this, and this is the file name which we loaded. So by default, it created plot underscore this n7 underscore fps. That's the plot name. So now I can. So yeah, I have the basic commands, for creating a plot. So because all of them were run over here, SVisual SVisual automatically ran all this. So now I can, and all this history has been saved in memory, SVisual's memory. So if I go to save, so you see, right, I had created this structure underscore viz.tickle. So I'm going to double click on this and I'll say, yes, I'm going to overwrite the file. So now, so this is the first step basically of creating your script. And same thing can be done for any other plots like XY plots. So now you see this is the script which are saved basically. And it has a lot of comment lines. I said earlier, hash starts, right? Hash starts a comment line. So these are all comment lines. So I don't need them. So I'm going to delete them. Okay. So I can put whatever comment I want here, right? So okay, we'll go into that later. And then these are the core SVisual commands. And as a result of running these commands, as I said earlier, every command will return a value. Okay. So this is what you see over here. So when you select a plot and all, so all these commands are echoing the return value of these commands. And here, of course, they are plot names and all that. So basically, we don't need, and what SVisual does is, since we don't need it in a script, SVisual will comment them out for us. But yeah, so we don't need it, so we can clean up our script like this, right? We can just get rid of this. And here you see, if I'm running SVisual from a project directory, right? So I don't need this full path. That way also I can clean this up, right? And then of course this create plot data set, when it creates a plot, it needs a data set. So by default, this load file will create a data set in which it stores the values. And of course this select plots command is there. So this is the first step in, you already have a script now. I mean, you have a basic script. Only thing is, it will work only on n7 underscore fps.tdr. So I'll close this, and you see here S process here created this n7_fps.tdr. That's a structure which is created by this in this experiment. Here I'm varying, let us say, the oxidation time, and again tomorrow Sushant will touch upon this. So here this node will create n8_fps.tdr. So now, so before going further, let us verify that whatever we did is correct. Again, I'll change this to batch mode. So essentially, we can verify whether the script which was created by SVisual is correct or not. So I can simply run this in using this visualizer icon now, because I changed it to batch mode also. So now the script is being run. The script which I saved, so that's what is being run. So you can now see, right, whatever I did. Now the script ran basically, and we can see the pre-process script also, right? So this is the script it ran. It pre-processed the command file, the input file basically, right? This one. This is the input file which was pre-processed by SVisual, and then it created a new pre-processed file, and you can see these are the commands which are actually run. Okay, so our commands are fine, but our problem is when I run this here, it will not load n8. I want it to load n8_mesh_fps.tdr, not n7. So what can I do here, right? So when I run this, it is loading n7_fps.tdr. When I run this again, it's going to load n7_fps.tdr. This structure, not this one. So then this is where the parameterization comes in. Okay, so that's what I showed here, right? So we can use this parameter. So in this case, I want output of S process, so I can use @tdr@. Okay, so instead of this, so I can have here @tdr@. Okay. Yeah. So and some other. So now if I check, if I pre-process this, you can see that instead of n7, it will have n8. Okay. So if I pre-process this node, so that @tdr@ was replaced by n8_fps.tdr. So that's the advantage of parameterizing our script basically. So now, but one more problem you see here, right? I want, let us say I want this, so this data set name also I want unique. I want unique data set names for each of these nodes. So again, so several parameterizations can be done, and I've already done it. So yeah, so this one. So then, once I have this basic file, okay, I can clean up the script, right? So as I said earlier, I can delete these comment lines. I don't need them. And then, so even this data set name I can parameterize. I can put a node number. I think Narendra already mentioned that this n, this @node@ will be replaced by the node number. So in this case, if this is my node, so n17, right? So it will be replaced by 17. So all these things I can use for parameterizing my script basically. So I'm just simply going to copy this whole thing over here in the interest of time. So now you see, so I am going to set the node number as n, and then I'm going to load a file which corresponds to the previous S process node, the TDR file, and then there's a dataset name. So again, I want unique dataset names for each script. Okay, each instance of the script. So I'm putting this struct $name. So this is something which can be done only in Tickle. I mean, so actually this name is not valid in any other language because you have these brackets and then you have $. But in Tickle, if you have continuous set of characters, right, and sequence of characters, Tickle by default will treat it as a string. So what it will do, as I'll show later, is it will replace this. So here, okay, let me just go through this pre-process file. So I'm going to pre-process this file now. So I'll open this pre-process file. So I think Naren already touched upon this a bit. So current node number is 17. So node is set as 17, is replaced by 17 in the pre-process command file. And then that is assigned to the variable capital N. That's what the set command does. and then we load a file. So you see, okay. So you see the correct file is going to get loaded. So n7 underscore fps.tdr, that is what is here, right? So I want to load this file when I run this script. I want to load this file when I run a script over here. So I'll pre-process this and I'll show you that script also parallelly. So again, you see, so this is my input script here, and then these are my pre-process scripts for both nodes. For each node, a different script is going to be created. That is what is going to be run when you run a particular node. So you see here you have n7 underscore fps.tdr, and then here you have n8 underscore fps.tdr, right? Both these both these TDR file names are different. Same way, I want to create a different structure each time. So again, here the dataset name will have struct, and in the brackets it will put 17. So this dataset name will be 17 struct 17. This dataset name will be 18. So then we of course create a plot. So this is a way of and then of course we have to give a name of the plot, and we have to use the dataset name when we create a plot. This create plot will either create a 2D or 3D plot depending on the file which you load. So if it's a 2D TDR file, it will load it will create a 2D plot. Otherwise, it will create a 3D plot. So now when I run both these instances, so you can see now I'll select both of them, and then I'll click on this pre-process run visualize the nodes together button. So yeah, so now you see the two plots are created now. So this is called, this has the label struct 17, this has the label struct 18. And if I go to this data view info loaded, I can see that two sets of data have been loaded. So you can see data set 17, 18, struct 17, 18. So these files were loaded in a single instance of SVisual, and then the data set was created based on our script. So we gave these names, right? Struct 17 underscore bracket $n. So these two data sets are created, and the dimensionality of these plots is 2D. And of course, we have these two plots. These are the plot names which got created. So, I mean, of course, they look a bit similar. I mean, they don't, because I just changed the oxidation time over here. So, but of course, slight differences I can show them. I mean, you can just double click on these. You can select both these frames or plots and then link them. And then I can create a cut line by selecting this. So I'm going to create a cut line. So as Narendra explained, this is down. Unlike our Cartesian coordinate system, which we see in textbooks, here the x is first of all on the up and down, I mean the vertical axis, and y is on the horizontal axis, unlike the normal Cartesian coordinate system that we're used to. So, and then of course x is pointing downward, it is increasing downwards, and y is increasing to the right. So now I want to take a cut line perpendicular to this y axis. So I choose this cut y, and then I can click over here, and then you can see there are slight. So both this net active concentration is active field, and that is what is getting plotted over here, right? So one is red, so this one is a red curve, and this one is the green. This one corresponds to the green curve, this plot. So you can see that two different, there are slight differences because of the oxidation time, and yeah. So yeah, so this is the way of parameterizing the script. That's the main point which I wanted to make over here. And of course, now I want to create this cut line, so I can again save the scripts and all, and interactively create my script again. Of course, for cut line it will not work. There is a slight twist over here, but yeah. So for that I've referred for cut lines and band diagrams and all that solar cell project which I was talking to earlier. So please refer to that one. So where are we now? So we have created a script interactively, we have parameterized it, we have cleaned it up a bit, we have parameterized it, okay? And now we want to modify the plot. We can make it look more pleasing aesthetically. And then of course, you should understand what are the parts or anatomy of a plot, whether it is 2D or XY plot. Normally, most of us know what are the different parts of a plot. So this is where we are now, like, so I created this plot, and then I'm going to show how to modify the plot by just making the legend more bolder or bigger and then white, basically. So maybe this looks good to me. So that's what I'm going to do. And then again, we'll save it in the script. And so here you see, right, different parts of a plot, like your plot. It's also called frame. So you can have multiple plots in the same SVisual instance, right? So that's what I'm showing here. So if you look at this, there are two plots in the same SVisual instance. So these are called plots or frames. And yeah, and then of course you have the axis, X and Y axis. So this is Y axis, this is X axis. This is called the legend, this whole thing. So you can see legend properties. So you can change the properties of this legend. It has a title and a font. So this is the title and this is the so you can change the font and font color and size. You can change the labels. So these are the labels. You can change them basically. Again, you can from black, I made it white and bigger. And these are the commands which got executed. I can change the orientation of this. I can make it horizontal also. So there are so many things that we can do. So again, I have, so let us see quickly how to do that. I'll just show one thing here. So again, I'm running this N17 node using this run visualizer nodes together button. So I don't like the position here, right? It's not overlapping. It's overlapping with this. I want to make it more central. So now I moved this legend and you can see the corresponding command over here, right? And then these are the legend properties which I can modify. So we need to select the element which we want to modify. So I selected this by clicking with mouse on the left mouse click will select the element. And you can see the legend here, right? If I want to modify the axis, I'll click on the axis and this I can modify the axis properties basically. So here I'll just modify this legend. So if I choose, so there are this is the title and the label. So I click on font, I can make it white. Maybe it gives me a better contrast and I can make it bigger. So I can have 1.6 over here and apply and close this dialog box. So you can see it has become bolder and bigger, bigger and then white. The same way I can do for labels. So maybe I want a bit smaller labels. So I'll make it 1.4 and then I'll say I can change the color again. So apply. So you can see and close it. So again, you can see that. So maybe this looks, I mean, I like it maybe. So now I'm happy with where it is, right? And then of course I can export it now. So since I like this image, I'll say, okay, file, export the plot. Okay, because I want to put it in my presentations basically. So if I say export plot, then I'll say, okay, here I can choose whether if there are multiple files, each one of them can be exported to a different PNG or TIFF file, image file basically, or even I can export all the plots to one file. I can set the okay. So then screen resolution, I can set the screen resolution. Is there a question here? Is someone asking? Okay, so the screen resolution I can set, and then when I set OK, I get this. Yeah, this sort of I can select the file name now. So let us say I want. So I'll put a name like temp. Okay, temp.png. Okay. So and when I say save, this temp will get created. Okay. So you see all these commands are getting stored here. So I'll save all these commands again in the same structure underscore viz.tcl. Okay. So I say yes. And if I look at my structure underscore viz.tcl, you see all my previous edits are gone. And now you have again all the outputs of running all these commands. So load script file, same as before, set legend property, and then export view. Again, the details are there in the manual. So to export view, yeah, so this is, so this is the new command, right? I mean, I exported the view and then I stored it in this temp.png and I specify the plot. Again, this is not parameters, as you can see, it will work only for one node and 17. And then the format I can specify as PNG. So, and then what if I want to visualize this now, right? So I can minimize this visual. I can make sure this folder is selected, this project. I click on this to open a terminal window. And then when I say display, I can use the display command to Unix command basically, and then temp.png, right? So when I do that, so you see, right? I mean, I can see the plot. Now I can take a screenshot. I mean, even as usual, I can take a screenshot and then I can take it to my PowerPoint and then insert this PNG file now. So this is one way of doing it. And now you see, again, all my edits are gone. So again, I have saved whatever edits I wanted to make in another. And here you see I'm splitting the screen by using these buttons the way I want, right? In this editor, many editors have this facility. So I've already created a script, and then I'll just copy paste this script here in the final script. And so again, these are the steps: clean up script, parameterize the script, modify the plot, and then export. This is a general workflow you can follow for creating your plots, basically. So I have combined. So you see, okay. So I'll show you both this. So what I did is I've cleaned up the scripts a lot. I have combined them, basically some of these commands. Yeah. So this is my final script. And so you see, there are so many things going on here. So even in export view, so this parametrization I already explained earlier. And when I click on the set legend property many times, right, to have the plot the way I want. So multiple times set legend property is there. So I can combine all of them together. And I earlier mentioned line continuation, right? So I can have, instead of multiple set legend property, I can have a single set legend property command and then use this line continuation to specify the argument the way I've done. And this looks much more cleaner, basically. So basically, even this position, I can shift here on the next line. And of course, I want it to be part of the set legend property command. So I put a line continuation. So this entire thing will be, this entire 4 lines will be one particular command. So I really don't need this. Okay. So this is my final script, and it looks much cleaner than what we see over here, right? And also I have parameterized this file name. Okay, for each node I want to create the structure, let us say. So instead of temp.png, I have this node number n. So again, as usual, tickle is a specialty. Again, this whole thing is treated as a string, and n, it'll create a file with file name n, followed by the, it will substitute the variable name over here, variable value over here, which could be 17 or 18. So n17 underscore doping.png, that's the file which will get created. So in SVisual or in Tickle, we don't really, in other languages or like C and all, we need to explicitly create strings like this by putting them in double quotes. But in Tickle, we don't need to do that. So in case there are no spaces in the string, we can easily create a string without the double quotes, basically. And of course, this variable substitution is going to happen over here. It will replace, SVisual will, Tickle will replace this value of n with the actual values like 17 and 18, depending on the node which I'm running. And of course, yeah. And same thing, as I said earlier, is happening over here also. And if we are doing this operation repeatedly, this export view, if already this PNG file exists, then SVisual complains it can't do the operation. So we have to use this overwrite option or overwrite argument also with this export view command. So then I'll just replace this whole thing on the left hand side. This is our actual script, which I've cleaned up and modified and parameterized. So again, I'll run these now, these 2 nodes. I'll clean. So to clean up the output, I can just go to N17 and press the del key, or I can go to right click and then press the del key over here. Press on delete somewhere. There should be cleanup. Yeah, you see this cleanup over here, right? And these are the shortcuts. So I can clean up like this also. So it will clean up all the out files and the pre-process files which are created by SVisual or any other tool. So now I'm going to run both of these and let us see. I selected both of them and press Control R. So for running the nodes, basically. And you can see this is now blue because the project is running, and green and then blue. So this is running, this is ready to run. Okay, so now you see, I showed you one way. So yeah, so if I click on this, I can see, right? Okay, yeah, I'm just checking. So we can always first pre-process the project and then make sure that we have the correct script over here. So you see the script is correct, the modified script is there basically. So whenever I change the script, I pre-process the project first and then check whether I'm running the correct script or not. And then of course, one more thing we need to do, if you want to create animations or if you want to create plots, right? Also, if you want to export these files, you need to use this -bx option. So any options when as usual runs, like as usual -b or something like that can be specified, or any specific release I want, all those options can be specified in this command line box, and that is what is going to be used basically over here. So let us see. And that's what I've written in this slides over here. Like, so you see this -bx option. So I'll just close this and I'll save it. And so when I run these two again, now earlier the image was not exported basically because I had not used the -bx option. So you see this -bx option is being used, -b option is being used when as usual runs. And now the images are going to be created basically. So now, yeah. So you see this N17 and .png got created, and even N18 got created over here. So now you see, right, if I select in this also, I can visualize in this node explorer, I can visualize the structure. Of course, it may not be good, but at least we know what is getting created over here as a result of running the script. So that was about how to create scripts interactively. So just to summarize again, we parameterize the script, right? But before that, basics are load file and then create the 2D plot using the file which we loaded. And then of course we select the plot and then we modify the plot based on how we want to look, how we want it to look. And then of course we explore the plot. This step you'll find only in case we want to, I mean, this you need only when you want to create presentations, insert the picture, I mean, create pictures and then insert them in your presentation. Otherwise, in most of the application library project, you won't find this step essentially. So coming back to the presentation, I've summarized all this in this presentation basically. Yeah. And then, so a few more concepts here in TDR file, I've been using them without specifying them. So we have a file, right? I mean, the TDR file is getting created either by S process or S device. And then it contains one or more data sets. And these data sets are nothing but they are collection of fields, the scalar and vector fields that we have saved when we did the simulation. And these are associated with the geometry, that means the device, basically the structure of the device. That's what I mean by geometry. So file contains one or more data sets, and these data sets contain fields basically. And this field is what we plot, whether scalar or vector. And so field is nothing but an array of values, and there are scalar and vector fields. So that's what this diagram shows, right? We have a file which consists of multiple data sets, and then of course it contains multiple fields basically. And yeah, so this is just, so these are the fields, right? So we have scalar field. So because it's from S process, we don't have vector field, but we can have even tensor fields. So so scalar field, vector fields, and then of course all this I had already showed data sets. So file is loaded and the data structure is created. And of course, these are the fields over here. That's the classification here. So this is just a summary of what I showed using this creating 2D plots. So yeah, so Prince sir, are you there? Hello.
Yes, sir.
So can we continue for some more time, or should I stop here, or because I have a few more slides on tickle basics. So
Sir, your voice
I mean, I think I need another half an hour.
Okay. So if if we can schedule break, you can schedule no issues. How much time it will take, sir?
At a half an hour, let us say. I'll complete the remaining part in half an hour.
Okay, fine then. Yeah. Yes, sir. Please
So
go ahead, sir.
So should I schedule a break now or should we continue?
Depends upon you, sir. If you want, you can schedule, sir.
Okay, so maybe it's 1:15, right? So maybe we
Yeah.
meet by 1:30. Is that, if that is okay with all the participants?
Yeah.
So I mean, so
depends
far we have all the
like-
tools we need for creating a script. I'm just going to show you how to make it more powerful by introducing some of the very few tickle concepts, basically. Like the set command and all this I said, right? So yeah, some of those concepts I'll highlight, and then we can stop, basically.
Yeah. After that, there will be some questionnaires also from the participants.
Definitely.
Yeah.
So I'll schedule a 15-minute break then, or so 1:30 we'll meet.
Yeah, sure. 20 minutes we can schedule, sir. After that, we can continue.
20 minutes. So we'll meet at 1:35 then. Okay.
Yeah, sure, sure.
Thank you. Bye. I'll see you soon. Hello. Hello, Prince sir. Hello. Yeah, it's 1:38, so I'll start. I hope my screen is visible now.
Yeah, sir. Visible, sir.
Okay, thank you.
Yeah.
So we saw about concepts about 2D plots, right? Now I'm going to talk about this 3D. So this is what we covered earlier. File has data sets and data sets has fields. So now I'm going to talk about how to create this 2D plot briefly. So to create a 2D plot again, I'll not bother about this. Yeah. So 2D plots can be actually, we can work with 2D plots in two ways. We can either, I think some slides are messed up. Okay, here it is. So similar to the diagram I showed you for 2D plots, now for XY plots also we have the same concepts. Instead of fields, we call them variables now. So basically a file, it contains one or more data sets. And then, yeah, so this data set consists of, it's a field. So it consists of variables, that's the terminology we use here. So field is nothing but mathematically defined function, right? I mean, mathematically we define it as a function which is defined at every point in space, in the 2D space or 3D space over the simulation domain. And this PLT file contains the terminal characteristic currents and voltages for all bias points. We are ramping the drain voltage, let us say, or gate voltage, and measuring the drain current, right? So those are called variables, basically, those terminal quantities. And so they are what I mean, the data set is made up of those variables, basically. And to create curves, this IDVG curve, drain current versus gate voltage curve, we need to use this variable. So basically, this curve is nothing formally but a collection of points or data points, and it is composed of two variables, which define the x and y axis of a plot. So let us say I have drain current and gate voltage. I'll be plotting drain current on the y-axis and gate voltage on the x-axis. So more or less the concepts are similar. And similar to, I'm not going to spend time on this in the interest of time. I'll just briefly talk about how to create this XY plot. Same methodology can be followed. We create it interactively, and already Narendra gave a demo of that. So we just load this PLT file broadly. So yeah, and then we create the plot. So here we need to, and you'll see when you see the echoed command, it has the option 1 minus this 1D. So we need to create a 1D plot basically. And then we set the plot properties, we create the curve. So here I'm plotting gate auto voltage versus drain current. And then we again set the curve properties. And then we carry out the extraction, parameter extraction, like this VTGA, which you see over here. So to carry out the parameter extraction, we need to load the extraction library using this load library extract command, load library, and then load library is the SVisual command, and then extract is the name of the library. So that's what we load. And then this particular lib set infodef procedure is controls the output messages which you see, the amount of output messages which you see. So in case of error, you can set it to a higher number. The higher the number, the more output you will get. So I'm using 1, which is the default actually over here. You can set it to 0, 1, 2, 3. So 0 means minimum message you will see in the out file, and 4 means you will see a lot of messages. So normally we keep it at 1. And then we need to get from the variables, we need to create tickle lists. So again, I'm not going to cover tickle lists, and then that is again there in the TCAD CentOS tutorial. So this get variable data SVisual tickle command, if we use that within the square brackets, we'll get the list of voltage values, get voltage values, and they'll be stored in this VGS variable. Same thing for drain current. So the drain current values will be stored in this IDS variable, and here we specify the variable name, which is gate, contact name, and the outer voltage, that is the quantity name. Here it is drain, the contact name, and the variable name, which is total current, and of course the dataset name. And that is how we'll get this 2 tickle lists, and we pass on those tickle lists to this extract VTGM procedure. This is a general way of extracting quantities. So here we are passing in this. So these are keywords here for extract VTGM, and many of them have the same keyword like voltage and current values. So we have this gate voltage values and drain current values, which are passed on to the extract VTGM using this flexible dash syntax, which I spoke about earlier. And then this is the name of the extracted variable. So the values, the threshold voltage value, which will be extracted as a result of this procedure, will be saved in a variable called VT, which is specified using this out keyword. And then the name. So while printing the value in the SW variable table, we'll use a particular name. So here it is VTGM and the value, right? So this value is obtained from this VT variable, and this VTGM, the name of the variable, is specified using this name keyword basically. So that is how it works. So we pass on 2 tickle lists, and then the gate and drain current values, gate voltage and drain current values. We specify the variable name in which the threshold voltage value should be saved, and we specify the name which should appear in the SW variable table. So this is general syntax for most of the extraction library procedures basically. So yeah, here I'm just showing. Okay, you have this. I've loaded this data set, a file called plot, called this idvg n52.plt, and then this plot is created, plot idvg, right, as a result of this create plot command over here. This is the load file command, right? I'm loading the file, and then the dataset name plt lin, which is there over here, this one, and then creating a plot. And then so this is the variables I was talking about earlier, right? And I think Narendra only showed this gate. So if I select gate, outer voltage over here, and then x-axis, so that way I can select these variables basically. And then yeah, so that is about creating XY plots. And of course, we have many scripts. We have huge number of scripts. You can always copy paste those scripts instead of creating your own, scripts. And then of course, you have to modify those scripts based on your needs. Basically, you can use them as it is if it works for you, or you modify them. And I was earlier talking about this, how to visualize multiple nodes together, right? So for that, we need to make some modifications to a script. So for example, here I can visualize 4 nodes basically here. I'm visualizing the drain current versus gate voltage of a NMOS at low bias, at low drain bias, high drain bias. Same thing for PMOS, low drain bias, high drain bias. With all these four curves from these four nodes from this project, which is the CMOS calculation project, from this I can visualize in a single plot. So what I need to ensure is that I create a single plot. Whenever I run all these four nodes, I should create the same plot for this to work out, right? So the plot name should be unique, and even the dataset names should be unique here. So, so every time I load a PLT file, I should have a different file name. Sorry, dataset name over here, as you can see over here, right? So how do we do that? We have this common name here, plot ID VG, in our older scripts. So we need to make sure we have a unique plot name, which is same in both script over here and script over here. In both these scripts, I should have the same plot name, and then even this curve name. So here you can see on the left hand side, this will not work the way I want it basically. So it will work only for one node. I mean one series of nodes, one column it will work basically this script. But if I want to use SVisual, I mean two different instances of SVisual to create these plots the way I've shown here, then we need to modify. This is completely parameterized for a particular column or SVisual instance basically. So you see here, right? I mean, when I'm loading it, yeah, so this PLT $lin, even this needs, this I've already shown, right? This is needed. So we need to have a unique dataset names, and then of course we need to create this plot only once. So for that we say, okay, we search through the list of plots which SVisual has so far created, and then if that plot doesn't exist, we create that plot over here, and we also set the plot properties. Then we select the plot basically. And then of course this part remains the same. Again, dataset names should be unique, and then even the curve names should be unique. This condition is there even for all sorts of parameterization, whether it's a single SVisual node or two SVisual nodes. This one and this one remains the same, the dataset name and the curve name. But the plot name has to be same also for both SVisual tool instances basically. So this way we can create powerful scripts. And of course, as I said, you don't have to do it on your own. You just copy paste whatever we have, but at least you should be able to understand the scripts to modify based on your needs. For example, here, I mean, it's so you can see, right? I hear drain current, and then I need a Greek symbol over here. Default unit of current is ampere per micron, and I want to print micron symbol. So for that, I can use this /Greek m/Greek symbol, and this m will be printed as mu. So yeah, so we need these scripting capabilities basically to create our curves. And of course, most of the application library projects have this, especially CMOS characterization project in CMOS folder in the application library, PDSI project, all those have it, all have these sort of capability. And so so that is regarding creating plots, and I'll touch briefly on some basic technical concepts, and then of course we can wind up. So I'll only touch upon those concepts which are not there in the TCAD CentOS tutorial, or which are touched upon briefly in that tutorial. So I've spoken about this multiple times. So we have this set command, and you create a variable just by saying, so the general syntax is set variable name and value. So you use it to create a variable. So the value which is specified is stored in this variable. So basically, if I say set I3, Tickle will create a variable called I and store the value 3 in it. And same thing we can do for a variable called pi, and you can see these values are getting stored here. Here, set message, I'm using explicitly double quotes here for strings because there is a space over here. So that's the reason I'm using, but in many cases, even this also works out basically without double quotes. So just to be clear, I put double quotes over here, and this is how it is getting stored in memory. And you can see, right, whether I put 3, which is an integer, or a floating point value, internally it will get stored as a, I mean, Ticker is implemented in C, so appropriate data structure will be used to store these numbers by Tickle basically. And to reference the value, we need to use this dollar symbol, which is not there in other languages, right? So in something like Python, you can just say x equal to 1, and then you can simply use x instead of $x. But in Tickle, we need to use this dollar symbol to access the variable value. So puts dollar message, so set message to hello world, and then puts message. If I say puts dollar message, then the value of this, basically the string hello world is going to get printed. So yeah, and then so there are different substitutions which are available. 3 types of substitutions are available in Tickle. So so this variable substitution I already discussed, it is triggered by $. So whenever Tickle sees $ in the script, it will replace the value with the variable name. So it will assume $I. So this is up to underscore, right? After a special character starts, it will stop looking at it as a variable name. So here it will treat I as a variable name, and so if I is 1, so then it will this variable name is actually should be 1 here. So I can so we need to delimit also. So one is variable substitution, so that is triggered by $. But when you have $I_1, then it will treat the variable name as I_1. It doesn't know to stop at this I. I want only the value of I to be substituted, not of I_1. This again you need to Tickle. So what I need to do is I need to delimit this I with braces, and that's what I had shown earlier also. So what it does is when it sees this $braces I, it will replace only the value of I. It will not look for I_1. So the value of I is 1. So this 1 will be put over here. So I'll have 1_1 as the value over here when I'm doing some computations. You can see that example over here, right? So if I say puts I is 1 and then puts $braces I, I'm delimiting it. I'm saying that only I is the variable, not I_1. That's not the variable name. And you can see it is 1_1, the output here. So this is variable substitution, which is triggered by $. And there's something called command substitution. So if you put commands inside square brackets, okay, so this whole square brackets will be replaced by the result. So the output of this is can be stored basically in a variable. That's the whole purpose of having this square brackets, and which we saw earlier also, right? So if you have this in the extraction, we had square brackets. So what is happening is the return value of this get variable data is a list, and because you have square brackets here, you command substitution takes place. So whatever is the output of this get variable data, that is what is being put over here, and that is what is getting. So that's the return value of get variable data, and that is stored in this VGS variable basically. So that is command substitution. So yeah, so expression 2 plus 3 will give me 5, and in Tickle we need to use expression. You can't say just 2 plus 3 and then get the value. So you need to type expression command and then 2 and 3. So you see, right? I mean, this returns 5, and then 5 is stored in this Z basically. And the third substitution is backslash substitution. So in case I want to print certain characters like this, let us say for some reason I want to print this square brackets in a string, or this braces which has special meaning in a string, or /n which is new line character in a string, then I can escape it with a backslash. In that case, I can have those characters inside a string basically. So this is just for printing these special characters in a string. So this is called escape sequence in a programming language like C. Yeah, but here it's called backslash substitution. So how does Tickle interpreter evaluate this command? It does it in 2 steps. So what it does is it breaks the command into words. Okay, and then it, so earlier also I mentioned that, right? For example, set message hello world. This has 3 words. So the first word is the name of the command, right? Set message hello world. So there are 3 words which are separated by white spaces, and then it will perform substitutions. But here, of course, there's no $, there is no square bracket, there is no backslash in this command, right? So then there are no substitutions which are performed here. And of course, the first word is used to locate a command procedure. So here the command is set, and remaining words of the command are passed as arguments to the command procedure. So this set command has 2 arguments, message and hello world, or 2 inputs, message and hello world. And then, of course, what is the result of running that command or invoking that command? So basically, Tickle sets the value of the variable message to the string value hello world. Okay, and of course, it returns the value of the variable message. You can see the return value here. So this is what is happening behind the scenes. When you type this and press enter, this is what is all this is going to happen, and then this value is going to get printed. And then, of course, this is another example of I said earlier there is no substitution taking place in the previous example. Here I have set message to hello world, and because there's a dollar, there's an additional step. This variable step substitution is going to take place. Dollar message is replaced with the string hello world. So that's the main difference between the previous thing, previous set message hello world command and set puts dollar message command basically. So again here there are two words, right? Puts and dollar message. So this is a command name. This is the argument which is passed, but first it is replaced. This dollar, it triggers this dollar substitution and replaces this dollar message with hello world, and then it passes the argument hello world to the puts command. So many places these concepts are important. That's why I'm trying to explain here. And of course, we can group words. So whenever we need, we can put them in braces or double quotes. Two ways of grouping, braces and quotes. So there is a difference. So for some reason, let us say I don't want the substitutions to take place. So anything which is there in this braces, there will not be any dollar. All these three things which I said earlier, right? Dollar or variable substitution and in command substitution or backslash substitution. None of these will take place inside if you put something in braces. So here the dollar substitution will not take place. So this will print $i+1, not the value of I. But then if you want the substitution to take place, you can put in double quotes. So you can say $i+1. So if I is 2, then here 2 plus 1, that's the string which will get printed. Okay. So braces can be nested. We can nest these braces, but not double quotes. So only these braces we can have any number of, and this is used in many application library projects where you will see, right? So I want to say gate voltage and the units I want to specify using square brackets. Because it is square brackets, it will try to interpret V as a command, but it's just a symbol, it's just a string, right? So that's why we put braces around this gate voltage and then square brackets. So this command substitution is not triggered in this case because of the braces. Yeah, and of course, many examples you will find this. Okay, so you have this double quotes. In double quotes, we are putting a long label. So all of them here, of course, I want the substitution to take place. I want to print the type of the device in this label. Okay, so here I'm going to print IDVG lin. I want to print the type of the device. I want to print the gate length, the drain voltage. So that's why I'm putting this a big string having all this dollar type and LG is equal to $LG and VD is equal to $VD. Because it is in double quotes, all the substitutions are going to take place. And in this particular example, we'll have this values of type LG and VD getting printed as a label over here. Okay. So that's what here, this whole thing, double quotes inside this expression is getting evaluated this one. And for performing math operations, you need expression command, as I said earlier, and then you have to say expression says 3 plus 2. So this will give you the value 5. But again, if you want to store it in the sum variable, then you have to put square brackets so that command substitution takes place. And then the value of this is returned and stored in this sum variable. These are the normal arithmetic operators, integral. And of course, there is, as in other programming languages, C, you have difference between integer arithmetic and floating point arithmetic or operations. For example, 1 and 2 are treated as integers, so you have 0 here. Because as I said earlier, TCAD is implemented in C programming language. So this is integer division, right? 1 by 2. So the answer actually is 0.5, but truncation will be performed. So anything after the decimal point that will be removed and 0 will be saved. Same thing here. I mean, but here, because this is 2.0, this will be treated as a floating point operation, a real number, and then 0.5 will be saved over. So whenever you need to divide two numbers, make sure that you have this dot, you treat one of them as a decimal number. And these rules are similar to C programming language. And of course, this expression can be used for computing so many things. For example, here I'm computing fill factor and efficiency of a solar cell. Again, all this is, we are creating some variables and computing some quantities using this expression command. And of course, we have all this C programming language math functions which are included in Trickle. So the syntax to use that is again, so the function name is ABS. So I say ABS, and then in C we use round brackets to call a function. So absolute value of -1. And in Trickle, we need to use expression, right, to evaluate any expression. The absolute value of -1 is returned as 1 over here. And of course, we have this physical constant library also in SVisual Tickle. So we load it, and then we can access the values which are defined in this physical constant library. For example, pi is defined over here in this particular syntax. And for easier scripting, we can set it to a more concise variable value like pi. And I want to compute sine of pi by 2. So again, I'm calling this sine function using this round bracket syntax, which is different from Tickle, right? In Tickle, I would have used sine space pi by 2, but that is not how sine is implemented in this Tickle programming language. It uses the C math function basically, and that is why we have a different calling syntax over here. More details about this math functions are given over here in this URL. And this format command, as I said, is used for formatting the way it looks, the printed output. So I'll not go too much in detail, but yeah, it is useful for formatting commands. For example, I have this format command, and then this is similar to other programming language, %.2f. So I want 2 decimal places after the number and then the variable name. So if I do that, then I can get a value of 3.14. So the variable pi is defined as a very long, so many digits are there, but I want to see only 2 digits over here. So this is pi, the value of pi. So I specify the variable name. So the first argument is the format string, basically %.2f. And then the second argument is the variable which I want to print, basically. And so this is useful for extracting values to SWB table. So imagine I print all this to SWB table here. So such a long string of values will be printed. So I can control that using this format specifier, basically. So if I use %.4g, so you can see here it is total using 4 digits basically, and there are only 2 digits after. So this g corresponds to best of either floating point or exponential format specifiers. Again, there's a lot of material available online which you can read about this. So I think, yeah, I've explained about the extraction library. So I think that brings me to the end of my presentation then. So now we can take question answers maybe. Prince, sir?
Yeah, thank you, sir, for the presentation. There are 2 questions, I think, in the chat box.
Okay. Chat box, okay.
One from the PCL commands that puts and gets difference.
No, it's puts and gets. Okay, I don't know gets actually. So maybe gets is for getting the data. I don't know. Maybe. Yeah, it says it reads a single line from specified channel. So that means gets is for reading the data, right? Puts is for printing the data, and gets is for reading the data from.
Right.
I mean, so the user can specify the values, right? So I can write interactive programs. Of course, they are of no use for SVisual, but in general Tickle programming, gets can be used for getting the data interactively.
Yes, correct.
So what other question is there?
Some demonstration they are asking for with the example. I think you have covered that one.
Oh, okay. Yeah, creating a plot.
Yes.
Okay, yeah, here is a chat.
I think they can unmute themselves if they have any questions. They can ask.
Yeah, please unmute yourself if you have any questions.
The TDR file.
Yeah.
TDR file. There is one.
What is the question?
They want to call TDR file from the previous node. So
Yes.
how to use that node 1 or previous?
Yes, yes. So the simplest is what I showed here, right? I mean, so I showed this syntax, right? So if it is from S process, right, and then we use add TDR at, and if we use S device, if we want it from S device, right, in SVisual, So you're talking about S visual, right? Specifically. So it can be either way. I mean, so add TDR add. So let us say in S device, I want to refer to SD. From SD, I want this TDR file. So then I can refer in S device to TDR file using add TDR add syntax. And if I want to load S device data into S visual, I can use add TDR dat syntax. So does that answer the question?
So
And specifically, you can also say add previous add. I mean, then you have to use a longer syntax, you know, and then add previous add. That sort of syntax you will have to use. So this is a more concise syntax if you are using standard file names.
Excuse me, sir. Am I audible?
Yeah.
Sir, that's my question. Actually, if I am introducing any file, like I have introduced in S device and I was calling in another S device. So how can I call it? Like, should I use previous or node -1?
No, I mean, I would say use add TDR add. Okay.
Okay.
So let me show you that. I think Narendra covered this maybe briefly. So you see, right, this is a typical S device command file in which I am
Samir,
using
can
add
you
TDR.
share your screen?
Oh, sorry. I think I unshared maybe. Yeah, now I hope it's coming up. Yeah, it's taking some time to share. Is my screen visible?
No, sir.
Not yet.
Okay, let us wait.
Yeah.
Now it's visible.
Okay, now it's visible, right? So what I had is in the previous node, I have S process, right? Let me show you both. Let me show you only these two files. So in one node, I have this S process, okay? And here I could have SD, it doesn't matter. I mean, either way, I'll get from add TDR add the previously generated structure from SD or S process. So you see in S process, we are saving the structure, okay, and at node add using this syntax. And then we are loading this using add TDR add. So this is what I would recommend. So even if you use SD over here in the previous instance, you can use add TDR add. So the idea is that so if you look here, a TDR file which is generated by SD or S process will be loaded. So if there is a SD instance over here, let us say, then that SD structure will get loaded, not the S process. So the last tool instance, whatever it is, SD or S process, that TDR file will get loaded in S device. Okay, that's the idea over here. Is it clear? So to answer in short, please use add TDR add, this one. Is it clear? Any other questions?
Any plot from the previous file, then how can I call that? Like same here?
Yeah, so
The plot.
you want to call a plot in S visual?
Yeah.
So then you use add plot add.
Okay,
So what
sir.
happens is, let us say I put an S visual here, right here. So I can
Yeah.
simply use, but then you have to be careful. What is your file extension? For example, here the prefix is idvg underscore, right? So this
Yeah.
prefix I have to add. So I have to write it as idvg underscore add plot add. So let us see, that should be an
Okay,
example
sir.
here.
So I
Otherwise,
should be like quite.
yeah, you have to be a bit careful over there. So yeah, this should have it.
Okay, sir. Thank
So
you,
I
sir.
already have a pre-written script here. Yeah, so that's what you will see here. You see this, right? Because add plot add means let us say n7 underscore des.plt, but I have renamed it, right? I have added this prefix in my S device command file. So that's why I need to
Yes,
make
sir.
that change. Okay.
Hmm.
Yeah.
Yes,
So
sir.
this
Thank you,
corresponds
sir.
to this over here. Yeah.
Thank you so much, sir.
Anything else? So I think you'll have this recording, and later on you can go through the lecture again and try to maybe understand the concepts. And of course, please go to the tutorial, because I did not cover much of tickle because yeah, I was running out of time. So yeah.
Yeah, sure, sir. Also, sir, please share PPT with us also, so that we can share with all the participants
Okay, sure.
after
Yeah,
this
I'll do that.
session.
I'll do that.
So I think no more questions in the chat box. So I hope we can conclude the session in a minute.
Yeah, so there is a question. Yeah, if you have any issue in tickle, where will you get help? So TCAD tutorial is there, and then of course in SVisual tickle I showed how to get help using help command, right? And what else is there? So there is a question regarding Solnet. Yeah, so you need to basically, yeah, Amy Mac, username is Amy Mac. They've asked about Solnet. So you need to basically register through your professor.
Yeah, sir. Actually, they have the IDs. They need to talk to their PI and co-PIs.
Correct.
Yeah, for the login credentials.
Yes, yes.
So if still there is issue, you can like message us or can raise the ticket also.
Yeah. And when will
I will
this
share the
recording?
details in the chat box.
So this recording will be posted on the C2S website?
No, sir. It will be shared through CDAC web cloud link.
Okay. Okay. Yeah, I think no more questions are there, so maybe we can conclude the session.
Thank you. Thank you so much, sir. Sameer sir, Narendra sir, Ridhan sir. I think Sankalp sir is not there. So
Yeah.
thank you all the Synopsys team for connecting such a wonderful session. So I hope this session is fruitful to all the participants. And if you have still doubt, I'm sending the credentials where you can post your doubts and queries. So I have posted the details. So you can raise your queries over here. So we'll reply you back. So thank you, sir. Thank you once again.
Yeah, thank you. Thanks
Thank you,
everyone for
bro.
attending.
Thank you, everybody.
Yeah. Bye everyone then.
Bye, sir.